124 light-years distant, in the celestial expanse of Leo, a revelation is unfolding that could fundamentally alter our perception of cosmic solitude. Utilizing the advanced capabilities of the James Webb Space Telescope, researchers have identified chemical signatures within the atmosphere of a faraway planet that, on Earth, are exclusively produced by biological processes. The certainty surrounding this detection stands at an impressive 99.7%, leaving a mere 3 in 1,000 chance of it being attributed to random statistical fluctuation. This world, designated as an ocean planet, exhibits an atmosphere abuzz with molecules that are characteristically released into our own skies by marine algae. If you find this kind of discourse engaging, we encourage you to consider subscribing to our channel. Prepare yourselves. What follows will undoubtedly challenge your most deeply held assumptions about the existence of life beyond our planet. Envision this: a planet traversing the face of its parent star. For a limited duration, a minuscule portion of the star's illumination filters through the atmosphere of that distant realm before reaching our telescopes. Within this light lie profound secrets. The James Webb Space Telescope meticulously captures this stellar light and disperses it into a dazzling spectrum of colors. Each distinct chemical element present in an atmosphere absorbs specific wavelengths of light, leaving its unique mark. Methane, for instance, effectively absorbs certain red light frequencies. Carbon dioxide, in turn, absorbs particular infrared wavelengths. Water vapor also leaves an unmistakable signature. This analytical method, known as transmission spectroscopy, functions akin to deciphering a complex barcode embedded within starlight. This scientifically validated technique has been successfully employed to study the atmospheres of numerous exoplanets. As a planet transits its star, the Webb telescope detects the resulting diminution in the star's brightness. More significantly, however, it captures the telltale molecular fingerprints imprinted on that light by every chemical compound suspended in that alien atmosphere. This process is exceptionally precise. The telescope is strategically positioned 1 million miles from Earth, far beyond the distorting influence of our own atmosphere, ensuring an unobstructed view. Its mirrors are meticulously coated in gold, optimized for capturing infrared light, the spectral region where these molecular signatures are most pronounced. What elevates this particular discovery to revolutionary status is the Webb telescope's extraordinary sensitivity. It can discern chemicals present at concentrations as low as parts per million. To illustrate, this would be analogous to pinpointing a single drop of ink within an Olympic-sized swimming pool. The data manifests as intricate graphs, displaying characteristic dips and peaks at specific wavelengths. Each discernible dip signifies a particular molecule absorbing light. By meticulously matching these spectral patterns, scientists can definitively identify the constituent chemicals. Methane, for example, exhibits 4 distinct absorption bands. Carbon dioxide presents 2 strong features. Water leaves behind 3 clearly identifiable marks. The James Webb Space Telescope employs 2 sophisticated instruments for this critical work. The first, known as the Near-Infrared Spectrograph, NIRSpec, analyzes wavelengths ranging from 0.6 to 5.3 microns. The second, the Mid-Infrared Instrument, MIRI, examines wavelengths between 5 and 28 microns. Together, these instruments provide a comprehensive profile of the chemical composition of distant planetary atmospheres. When scientists directed the Webb telescope towards this ocean planet, their initial expectations were to detect methane and carbon dioxide. These gases had previously been identified by the Hubble Space Telescope, although the older instrument's precision was considerably limited. What they subsequently discovered prompted them to reevaluate their instruments on no fewer than 3 separate occasions. The spectral analysis revealed absorption features that corresponded with only one specific compound, dimethyl sulfide, or possibly its close chemical relative, dimethyl disulfide. These two molecules share remarkably similar spectral signatures within the observed wavelength range. The detected signal appeared prominently at wavelengths between 4 and 5.2 microns. Multiple absorption bands aligned perfectly with laboratory-derived measurements of these sulfur-containing compounds. The intensity of the signal indicated concentrations exceeding 10 parts per million. For context, Earth's atmosphere typically contains these molecules at concentrations below 1 part per billion. This implies that a source on this distant world was generating them at rates thousands of times greater than observed on our own planet. However, the subsequent findings are even more astonishing. Scientists conducted the observations twice, utilizing distinct instruments. Both instances yielded the identical molecular signature. The probability that this result occurred through random chance has been calculated at merely 0.3%. In statistical terminology, this represents a 3 sigma level of certainty. While not yet sufficient to definitively declare a discovery, it far surpasses mere coincidence. To achieve the gold standard of 5 sigma certainty, which signifies a statistically robust scientific discovery, requires only 2 or 3 additional observation windows. These could realistically be obtained within the coming year. This naturally leads to the crucial question: what could possibly be responsible for producing these molecules in such extraordinary quantities? On our planet, dimethyl sulfide has a singular, well-established origin: life. Specifically, it is produced by microscopic marine organisms known as phytoplankton. These minuscule algae synthesize a compound called dimethylsulfonneopropionate during their growth phases. Upon their demise or through the action of bacteria, this compound undergoes a transformation into dimethyl sulfide. This volatile gas then escapes into the atmosphere, becoming detectable. Take a stroll along any coastline, and you will invariably detect that sharp, slightly pungent aroma in the air. That is dimethyl sulfide. For decades, scientists have diligently searched for any non-biological mechanism capable of producing this molecule in planetary atmospheres. Thus far, no viable pathway has been identified that operates at significant scales. Laboratory experiments can, under highly specific conditions, and through reactions involving methane and hydrogen sulfide, generate trace amounts of this compound. However, these production pathways are inherently inefficient. They necessitate precise reactant ratios and yield dimethyl sulfide at concentrations considerably lower than what is observed on Earth, let alone what the Webb telescope has detected on this distant exoplanet. The significance of this finding lies in the fact that most potential biosignature gases present ambiguities. Methane, for instance, can be attributed to volcanic activity. Oxygen can be generated through the photolysis of water molecules by ultraviolet radiation. Phosphine, in turn, might form during intense storms on gas giants. Each of these gases possesses at least one known abiotic pathway that complicates interpretation. Dimethyl sulfide and its counterpart, dimethyl disulfide, stand apart. Their chemical synthesis is intrinsically linked to specific biological pathways that no known geological process can replicate at high concentrations. Furthermore, this molecule has a limited atmospheric lifespan. In Earth's atmosphere, dimethyl sulfide degrades within a matter of days, succumbing to the effects of sunlight, oxygen, and hydroxyl radicals. This implies that any detectable dimethyl sulfide must be continuously generated. On Earth, phytoplankton blooms and subsequent decay create cyclical releases, replenishing the atmospheric supply. The very fact that we can measure its presence confirms an ongoing production mechanism. Now, consider the implications of detecting this gas on another world at concentrations 10,000 times greater than those on Earth. The mathematical conclusion becomes inescapable. Whatever the source, it must be exceptionally potent. Some process is generating dimethyl sulfide or dimethyl disulfide at a rate exceeding its rate of chemical decomposition. On our planet, Our oceans teem with trillions upon trillions of phytoplankton, working ceaselessly. To account for the concentrations detected by Webb would necessitate life on a scale that is almost beyond comprehension. Theoretical research published prior to the Webb observations had actually predicted precisely this scenario. Scientists modeling hypothetical ocean worlds with hydrogen-rich atmospheres calculated that if life were present, dimethyl sulfide would accumulate to significantly higher levels than observed on Earth. The abundant hydrogen in the atmosphere would effectively retard the degradation pathways. Microorganisms could flourish within warm subsurface oceans, and their metabolic byproducts would gradually accumulate. The predictions from these models align almost perfectly with the observational data. This represents a theoretical framework supported by sophisticated modeling, not yet a confirmed empirical fact. However, the striking concordance between these predictions and the observations instills a sense of cautious optimism among scientists. One researcher at Cambridge has posited that, given all known characteristics of this particular planet, an ocean world teeming with life presents the most compelling explanation for the observed data. Nevertheless, caution remains the paramount watchword. The next critical step involves systematically ruling out every conceivable alternative explanation, however improbable it may seem. What if some unknown mechanism, entirely beyond our current understanding, is capable of producing these molecules? When scientists state they have achieved 99.7% confidence, they are referring to statistical certainty. Specifically, it means the detected signal has only a 0.3% probability of being random noise. In statistical parlance, this is termed 3 sigma certainty. Imagine flipping a coin repeatedly. If you were to achieve 10 consecutive heads, you might reasonably suspect the coin is biased. This scenario approximates a 3 sigma event. However, if you were to achieve 20 consecutive heads, you would be virtually certain the coin is not fair. This would represent a 5 sigma event. The universally accepted benchmark for declaring a scientific discovery is 5 sigma. At this level of certainty, the probability of error plummets to less than 0.00006%. Particle physicists relied on 5 sigma validation when announcing the discovery of the Higgs boson. Astronomers employed it when confirming the detection of gravitational waves. For a discovery as profound as the potential identification of extraterrestrial life, nothing less will suffice. Currently, this remarkable finding rests at the 3 sigma threshold, undeniably exciting, yet not yet conclusive. Here is how this statistical assessment was derived. The James Webb Space Telescope acquired observational data revealing distinct absorption features at specific light wavelengths. Scientists then meticulously compared this data against theoretical models. One model incorporated the presence of dimethyl sulfide or dimethyl disulfide in the atmosphere, while another model assumed their absence. The model that included the sulfur compounds provided a substantially superior fit to the collected data. Rigorous statistical tests indicated that the probability of achieving such an accurate fit purely by chance, if these molecules were indeed absent, is precisely 0.3%. However, chance is not the sole potential source of error. Systematic errors can also mislead instruments. It is conceivable that the telescope's calibration may have experienced slight drift. Alternatively, thermal noise could have generated spurious signals. It is also possible that the star itself possesses unusual characteristics that coincidentally mimic the spectral signature of dimethyl sulfide. Scientists have dedicated months to investigating these potential confounding factors. They utilized 2 distinct instruments aboard the Webb telescope, and both instruments registered the identical signal. They meticulously examined observations of other planets to confirm the uniqueness of this particular signature. Furthermore, they developed and tested dozens of models positing alternative atmospheric compositions. None of these alternative scenarios provided a fit as compelling as the one involving dimethyl sulfide. To achieve the coveted 5 sigma certainty, further data acquisition is essential. Each observation window, during which the planet transits its star, lasts approximately 8 hours. Thus far, 2 such windows have been utilized. Scientists estimate that an additional 2 to 3 observation windows are required, translating to approximately 16 to 24 hours of telescope time, spread across multiple transits. The planet completes one orbital revolution every 33 days, meaning opportunities for observation arise with relative frequency. However, the Webb telescope is the most highly sought-after instrument in the history of astronomy, with thousands of researchers vying for precious observation time. Securing approval necessitates a stringent selection process. The lead researcher has officially submitted a request for supplementary observation time. A panel of experts will subsequently evaluate the scientific merit and cost-effectiveness of this proposal. If approved, confirmation of this discovery could potentially be obtained within the next 12 months. This timeline places us, at most, 1 year away from potentially confirming the existence of alien life. We could be just 1 year away from answering humanity's most enduring question: are we alone in the universe? But here is what makes this moment so electrifying. Even at the 3 sigma confidence level, even with the remaining uncertainties, we have unequivocally crossed a significant threshold. For the very first time in human history, we possess data from another world that is more readily explained by the presence of life than by its absence. This is an unprecedented development. What imbues this particular world with such unique characteristics as to produce such a potent signal? The planet orbits a star classified as a red dwarf. These stars are inherently smaller, cooler, and less luminous than our own Sunday. This specific red dwarf exhibits a surface temperature of approximately 3,184 degrees Celsius, a stark contrast to our Sun's 5,500 degrees Celsius. Furthermore, the red dwarf possesses only 45% of our Sun's radius. This translates to less mass, reduced heat output, and diminished light emission. However, a critical factor comes into play. The planet orbits its star at a significantly closer proximity to compensate for this reduced luminosity. Earth maintains an average distance of 93 million miles from our Sun. In contrast, this ocean planet circles its star at a mere 13 million miles. This places it approximately 167 times closer to its star, relative to the star's size, than Earth is to the Sun. Distance plays a far more crucial role than might initially be apparent. The intensity of starlight adheres to the inverse squared law. Doubling the distance reduces the received light by a factor of 4. Conversely, moving 10 times closer increases received light by a factor of 100. This planet orbits so closely that, despite its star's inherent dimness, it receives an amount of energy comparable to that received by Earth. Scientists refer to this orbital region as the habitable zone, the celestial band around any star where a planet, possessing the appropriate atmospheric conditions, could sustain liquid water on its surface. For our Sun, this zone extends from approximately 90 million to 140 million miles. For red dwarf stars, the habitable zone is situated considerably closer, sometimes extending only a few million miles from the star. This understanding is corroborated by decades of astronomical observations and sophisticated climate modeling. Temperature is not solely determined by distance from the star. Atmospheric composition plays a pivotal role. A planet enveloped in a dense atmosphere can trap heat through the greenhouse effect. Gases like carbon dioxide and methane are particularly efficient at this process, with water vapor also contributing significantly. The precise atmospheric mixture can maintain a planetary surface temperature even at considerable distances from its star. The planet Venus serves as a cautionary example of this principle taken to an extreme. Despite its closer proximity to the Sun than Earth, Venus would theoretically be a cooler planet if not for its overwhelmingly dense carbon dioxide atmosphere. As it stands, surface temperatures on Venus soar to a searing 470 degrees Celsius. This particular ocean world is characterized by a hydrogen-rich atmosphere. While hydrogen is less efficient on a per-molecule basis at trapping heat compared to carbon dioxide, its sheer abundance in this atmosphere more than compensates for this lower efficiency. Models suggest that the atmosphere may constitute as much as 6% of the planet's total mass. For comparative purposes, Earth's atmosphere represents less than 1/millionth of our planet's total mass. Such a substantial quantity of hydrogen generates a potent greenhouse effect, even with its lower per-molecule efficiency. However, this close proximity introduces a significant complication. The very proximity that facilitates the existence of liquid water also poses a considerable danger. Red dwarf stars are notoriously volatile celestial bodies. They are prone to emitting powerful stellar flares, sudden, intense bursts of radiation and charged particles that bombard nearby planets. These flares can, over millions of years, erode planetary atmospheres. They also inundate planets with high levels of ultraviolet and X-ray radiation, which are capable of destroying complex organic molecules and rendering planetary surfaces sterile. Despite these formidable challenges, this exoplanet appears to have retained its atmosphere. Observational data indicates the presence of abundant hydrogen, methane, and carbon dioxide. If the star were continuously stripping away the atmosphere, evidence of atmospheric loss would be readily apparent. The continued presence of these heavier molecules suggests that the planet has maintained its atmospheric envelope for a considerable duration. It is possible that its substantial gravitational pull aids in retaining the atmosphere, or perhaps the atmosphere itself is sufficiently dense to withstand the stellar onslaught. Alternatively, we might be witnessing a planet in a fleeting transitional phase before its atmosphere is irrevocably lost. The star itself is estimated to be approximately 2.4 billion years old. For perspective, Earth is 4.5 billion years old. This star system is therefore roughly half the age of our own. It is young enough that the planet may still be geologically active, yet old enough that any life that may have arisen would have had ample time to evolve. Now, consider what transpires when all these factors are combined with the most peculiar characteristic of this world, its orbital period. One complete orbit around its star takes a mere 33 Earth days. This translates to a planetary year lasting just over a month. Imagine celebrating your birthday 33 times faster than we do. By Earth standards, you would be over 1,000 years old by the time you reached your 30th birthday. However, this rapid orbital pace has profound consequences that ripple through every aspect of the planet's behavior. Firstly, let us consider the concept of seasons. On Earth, seasons occur due to our planet's axial tilt of approximately 23 degrees. When the northern hemisphere is tilted towards the sun, we experience summer. 6 months later, as it tilts away, we experience winter. This ocean planet likely possesses a minimal axial tilt, meaning seasons, as we understand them, would not manifest. Instead, any climatic variation would be dictated by the orbital path itself. This is where the situation becomes particularly intriguing. The planet's orbit is not perfectly circular. Rather, it is noticeably elliptical. Scientists quantify this deviation using a parameter known as eccentricity. Earth's orbit exhibits an eccentricity of 0.0017, signifying an orbit that is exceptionally close to a perfect circle. This ocean planet, however, possesses an eccentricity of approximately 0.09, making its orbit over 5 times more elliptical. This is a fact confirmed through precise measurements of its orbital timing. Consequently, the planet's distance from its star varies significantly throughout each orbit. At its closest approach, the planet resides approximately 12% nearer to the star than at its farthest point. While this might not seem like a substantial difference, the inverse square law amplifies this variation considerably. The planet receives roughly 43% more starlight at its closest orbital point compared to its farthest distance. Imagine the climatic implications if Earth's temperature experienced such wild fluctuations. Every few weeks, temperatures would dramatically spike and then plummet in regular cycles. Any surface water would be subjected to constant cycles of freezing and thawing. This creates a fundamental problem of stability. Life, as we currently understand it, requires relatively stable temperature ranges. Extreme thermal swings would make it exceedingly difficult for complex biochemical processes to establish and sustain themselves. Water could potentially freeze during one part of the orbit and then boil during another. Organisms would need to possess the remarkable resilience to survive both these extremes within the span of a single month. While extremophile bacteria on Earth demonstrate the capacity to endure a wide spectrum of temperatures, some thriving in boiling hot springs while others survive in the frigid Antarctic ice, requiring organisms to contend with both extreme heat and cold on a monthly schedule presents an entirely different biological challenge. Nevertheless, the dimethyl sulfide signal persists. If life exists on this planet, it must have evolved remarkable adaptations to this chaotic orbital rhythm. It is conceivable that the dense hydrogen atmosphere acts as a crucial thermal buffer, mitigating the most extreme temperature fluctuations. Alternatively, life might seek refuge in deeper oceanic layers during periods of intense thermal variation, awaiting a return to more stable conditions. It is also possible that the vast oceans themselves possess sufficient thermal inertia to prevent drastic temperature swings. There exists another significant challenge associated with such rapid orbital periods. When a planet orbits so closely to its star, gravitational forces become exceptionally intense. The star exerts a stronger gravitational pull on the near side of the planet than on the far side. Over immense timescales, this differential pull generates tidal forces that gradually decelerate the planet's rotation. Eventually, this process results in tidal locking, where one side of the planet perpetually faces the star in eternal daylight, while the opposite side remains in perpetual darkness. Scientists suspect that this ocean planet is tidally locked, although this hypothesis remains unconfirmed. If this is indeed the case, the day side would experience scorching temperatures, while the night side would be frozen solid. Only a narrow twilight band, situated between these two extreme hemispheres, might offer temperatures conducive to liquid water. Powerful winds would likely sweep across this boundary, as hot air from the day side rushes to fill the frigid void of the night side. The resulting weather patterns would be unlike anything observed on Earth. However, the presence of a thick hydrogen atmosphere could potentially alter this scenario. Computer simulations suggest that a dense atmosphere is capable of efficiently transporting heat from the day side to the night side. This could, in turn, create more habitable conditions across a broader expanse of the planet's surface. In the absence of direct visual observation of the planet's surface, scientists can only infer these effects. What is definitively known is that this world's diurnal cycles, or lack thereof, are fundamentally different from Earth's. How does a planet with a radius 2.5 times that of Earth manage to sustain conditions that might support life? The planet's radius is approximately 2.6 times larger than Earth's, making it a substantial celestial body. Its volume exceeds ours by more than 17 times. If one were to stand on its surface, assuming a solid surface exists, the gravitational force would be crushing, approximately 2.5 times stronger than Earth's gravity. Every step would feel as though one were carrying an additional replica of oneself on their back. This characteristic is confirmed through precise measurements of the planet's mass and size, which are derived from detailed analysis of its orbital mechanics. However, a planet of this magnitude presents a distinct challenge to our conventional understanding of planetary formation. Planets of such size typically do not resemble Earth. Instead, they more closely resemble Neptune. Our solar system features 4 rocky inner planets and 4 gas giants, with no intermediate categories. This ocean planet occupies precisely the missing classification. Scientists refer to planets of this nature as sub-Neptunes. They are larger than Earth, but smaller than Neptune. Thousands of such planets have been discovered orbiting other stars, yet we lack any examples within our own solar system that we can study up close. The fundamental mystery surrounding these sub-Neptunes lies in their composition. Are they rocky planets that have accumulated vast atmospheres? Are they icy worlds, akin to Neptune, that failed to attain full gas giant status? Or do they represent an entirely different class of planet, one for which we have no terrestrial analog? The answer to this question has profound implications for the potential for life to exist on such worlds. The planet's density offers crucial clues. Earth possesses a density of 5.5 grams per cubic centimeter, indicative of a composition primarily of iron and rock. Neptune, on the other hand, has a density of 1.6 grams per cubic centimeter, reflecting its composition of water, ammonia, and methane ices, encased within a thick envelope of hydrogen and helium gas. This ocean planet exhibits a density of 2.67 grams per cubic centimeter, positioning it squarely between Earth and Neptune. One prevailing theoretical model suggests the following structure. The planet likely possesses a rocky core, perhaps 3 to 4 times the mass of Earth. Surmounting this core would be a mantle composed of high-pressure ice, not the familiar ice found in freezers, but a form of ice that exists under extreme pressure and remains solid even at elevated temperatures. Above this icy layer, there might be a vast expanse of liquid water, capped by a substantial atmosphere of hydrogen and helium. It is important to note that this structural model is purely theoretical, derived from calculations based on the planet's mass and density measurements. The precise composition remains an open question. This theoretical framework gives rise to the notion of Hycean worlds. The term itself is a portmanteau of hydrogen and ocean. The underlying concept posits that planets possessing hydrogen-rich atmospheres and surfaces covered in liquid water could potentially sustain life, even if they are significantly larger than Earth. Such a hydrogen atmosphere would act as a thermal blanket, trapping heat through an enhanced greenhouse effect. The presence of liquid water would then provide the essential solvent for biological processes. Microorganisms could theoretically drift within these vast bodies of water in a manner analogous to how phytoplankton navigate Earth's seas. However, this proposition is not without its detractors, who highlight several critical issues. At the extreme surface pressures anticipated on such colossal planets, water might not remain in a liquid state. Instead, it could transition into a supercritical fluid, a state where the conventional distinction between liquid and gas dissolves. Picture a substance that flows like a liquid yet possesses the density of vapor. This state emerges at temperatures exceeding 374 degrees Celsius and pressures over 221 times Earth's atmospheric pressure. Should the surface temperature or pressure surpass these thresholds, the existence of liquid oceans becomes untenable. A segment of the scientific community argues that such worlds would be excessively hot. Climate simulations suggest that, given a dense hydrogen atmosphere and the intensity of the starlight received, surface temperatures could ascend beyond 500 degrees Celsius. At such extreme temperatures, any water would invariably exist as a supercritical fluid or vapor. The planet's surface might, in fact, consist of molten rock, a vast ocean of magma enveloped by a hydrogen shroud. If this were the case, the observed dimethyl sulfide signature would necessitate an entirely different explanation. Yet, alternative models present a contrasting perspective. These simulations propose that if clouds were to form in the upper atmospheric layers, they could reflect a sufficient amount of starlight to maintain a cooler surface. A high albedo, representing the measure of reflectivity, exceeding 90% could potentially preserve liquid water. The feasibility of such cloud formation, however, remains an open question. The unique chemistry of hydrogen-predominant atmospheres presents distinct challenges for cloud genesis compared to terrestrial conditions. What specific aspect renders the absence of certain molecular compounds a crucial piece of evidence? Earth's oceans harbor an estimated 25 trillion phytoplankton. These microscopic organisms freely drift in the sunlit surface waters, utilizing photosynthesis to convert carbon dioxide and sunlight into energy. They are responsible for generating approximately half of the oxygen we inhale. These organisms form the foundational element of the marine food web and are the source of dimethyl sulfide that one encounters at the seaside. That characteristic aroma in the air is largely attributable to these minuscule life forms. Phytoplankton produce a specific compound to regulate the salt balance within their cells. This compound acts as an osmolyte, assisting them in managing the salinity of seawater. Upon the demise of phytoplankton, or when bacteria colonize them, enzymes initiate the breakdown of this compound. One of the resulting byproducts is dimethyl sulfide. This gas is released into the atmosphere at an estimated global rate of 100 million tons annually. This is a scientifically validated phenomenon, directly measured through atmospheric sampling and satellite observations. The molecule's atmospheric lifespan is remarkably brief. Hydroxyl radicals present in the atmosphere readily react with it within days. Sunlight also contributes to its decomposition. It oxidizes into sulfur dioxide, subsequently transforming into sulfuric acid, which then coalesces into microscopic particles. These particles serve as nucleation sites for cloud formation. An increase in cloud cover leads to more sunlight being reflected back into space, thereby cooling the planet. Some researchers propose that this process establishes a feedback loop. Warmer oceans stimulate greater phytoplankton proliferation. Increased phytoplankton populations result in elevated dimethyl sulfide production. A higher concentration of dimethyl sulfide fosters more extensive cloud formation. Ultimately, these clouds contribute to planetary cooling. This hypothesis, while not yet conclusively proven, is a subject of considerable scientific discussion. Now, let us consider the implications of detecting dimethyl sulfide on another celestial body. The presence of this molecular signal necessitates a continuous rate of production. Something must be generating this compound at a pace that outstrips its rate of chemical degradation. On Earth, the collective metabolic activity of trillions upon trillions of phytoplankton cells barely sustains atmospheric concentrations of dimethyl sulfide at approximately 1 part per billion. To achieve a concentration of 10 parts per million, as observed on this hypothesized ocean world, would require a production rate 10,000 times greater. What could possibly account for such an extraordinary output? One potential explanation involves a vastly larger quantity of phytoplankton. If the oceans on that world harbor significantly more microbial life per unit volume than Earth's oceans, the mathematical correlation would hold. But what drives such a scenario? Perhaps the unique combination of a hydrogen atmosphere and the presence of liquid water creates exceptionally favorable conditions for microbial blooms. It is conceivable that nutrients are more readily available, or that the absence of natural predators permits unchecked population growth. Another possibility lies in fundamentally different biochemical processes. It might be that life forms on that world produce dimethyl sulfide directly, rather than as a mere metabolic byproduct. On Earth, phytoplankton synthesize dimethyl sulfonopropionate for one purpose, and dimethyl sulfide emerges as an incidental consequence. On a different world, life might employ dimethyl sulfide as a signaling molecule, a product of energy metabolism, or even as waste from cellular respiration. Divergent evolutionary pressures could lead to distinct functional roles for the same chemical compound. Furthermore, the contribution of bacterial life warrants consideration. On Earth, bacteria play a substantial role in transforming dimethyl sulfonapropionate into dimethyl sulfide. Specific bacterial species have evolved specialized pathways for this conversion. An ocean teeming with these bacteria, actively metabolizing organic matter, could generate immense quantities of dimethyl sulfide. The detection of dimethyl disulfide alongside dimethyl sulfide lends support to this idea. On Earth, dimethyl disulfide originates predominantly from bacterial metabolism, not directly from phytoplankton. The odor these molecules produce is potent and unpleasant. At elevated concentrations, dimethyl sulfide carries a distinct aroma reminiscent of rotting vegetables or decaying seaweed. Some individuals describe it as having a garlicky or sulfurous scent. Were one to hypothetically visit this ocean world and inhale its atmosphere, assuming the hydrogen itself did not prove lethal, the stench would be overwhelming. Envision standing downwind from an immense algal bloom, spanning millions of square miles, all simultaneously releasing dimethyl sulfide. This is the likely olfactory experience of that planet's air. However, the sensory aspect is secondary to the scientific significance. The crucial question revolves around what this molecule reveals about the potential for extraterrestrial life. For decades, scientists have rigorously sought any non-biological mechanism capable of producing dimethyl sulfide in substantial quantities. No such pathway has been discovered. Every known process necessitates the involvement of living cells. If this principle holds true on that distant world, then we are observing a chemical fingerprint of life, illuminated by starlight. How could concentrations reach 10,000 times greater than Earth's? Earth's atmosphere contains dimethyl sulfide at less than 1 part per billion by volume. Collecting air samples above the ocean will reveal its presence, but only just barely. The molecule degrades rapidly. Its average atmospheric lifespan is approximately 1 day. This fact is firmly established through meticulous atmospheric chemistry studies. Sunlight actively degrades it. Hydroxyl radicals tear it apart. Oxygen transforms it into sulfur dioxide. The sole reason we detect it at all is due to the constant replenishment by phytoplankton. This ocean world exhibits concentrations exceeding 10 parts per million. That represents a disparity of over 10,000-fold. To put this into perspective, imagine if Earth's atmospheric carbon dioxide concentration were to surge from its current 400 parts per million to over 4 million parts per million. The entire planet would become uninhabitable within days. However, dimethyl sulfide does not function as carbon dioxide. It does not drive planetary warming in the same manner. Its primary impact is chemical, not thermal. What could possibly account for such elevated concentrations? One plausible explanation involves the planet's hydrogen-dominated atmosphere itself. On Earth, oxygen constitutes approximately 21% of our atmosphere. Oxygen is highly reactive and efficiently breaks down dimethyl sulfide. This ocean world, however, possesses a hydrogen atmosphere with negligible oxygen content. Hydrogen exhibits considerably lower reactivity towards dimethyl sulfide. Consequently, the destruction pathways effective on Earth might be largely absent or significantly less potent. The molecule could persist for weeks or months, rather than mere days. A longer atmospheric lifespan necessitates a reduced production rate to maintain high concentrations. If dimethyl sulfide endures 10 times longer, only 1/10 of the production rate is required to achieve the same atmospheric level. If it persists 100 times longer, 1/100th of the production rate suffices. Scientists engaged in modeling this ocean world have calculated that within a hydrogen-rich atmosphere characterized by high carbon dioxide and low oxygen levels, dimethyl sulfide could persist for a considerably extended period compared to its terrestrial counterpart. This is a theoretical construct, yet it is grounded in established principles of atmospheric chemistry. However, Even accounting for an extended atmospheric lifetime, the sheer magnitude of the required production is staggering. One research team has estimated that a biogenic flux, the rate at which organisms generate the gas, thousands of times greater than that provided by Earth's oceans would be necessary. This points towards either a far greater density of life per unit volume, or significantly more efficient dimethyl sulfide production pathways, or a combination of both. This is where the connection to carbon dioxide becomes relevant. Observations revealed approximately 1% carbon dioxide in this planet's atmosphere, a concentration 25 times higher than Earth's 400 parts per million. Elevated carbon dioxide levels can profoundly influence the metabolic processes by which organisms process sulfur compounds. Certain terrestrial bacteria utilize carbon dioxide in their metabolic pathways. It is conceivable that on this ocean world, the abundance of carbon dioxide drives distinct biochemical pathways that result in a higher production of dimethyl sulfide per cell. There is an additional contributing factor: temperature. Temperature directly affects the rates of chemical reactions. Warmer water accelerates metabolic processes. If the oceans on this world are warmer than Earth's, organisms might exhibit faster growth rates, more rapid reproduction, and consequently, quicker generation of waste products. The average temperature of Earth's oceans hovers around 4 degrees Celsius. Models suggest that the surface temperature of this ocean world could range from 10 to over 50 degrees Celsius, depending on cloud cover and the intensity of the greenhouse effect. At 30 degrees Celsius, biological processes operate several times faster than at 3 degrees Celsius. Consider the combined impact of all these factors. A hydrogen-rich atmosphere that retards the degradation of dimethyl sulfide. Abundant carbon dioxide influencing altered metabolic pathways. Warm oceanic waters accelerating biological activity, potentially leading to a higher biomass density than Earth's oceans. The multiplicative effect of these influences could readily explain the dramatically higher concentrations observed. Each factor, acting independently, might contribute a twofold or fivefold enhancement. When combined, they multiply rather than simply add. For instance, a twofold enhancement multiplied by a fivefold enhancement, then by a threefold enhancement, and a fourfold enhancement, results in a cumulative effect of 120 times. Introducing a few more contributing factors could easily push the cumulative impact to 10,000 times. However, critics pose a counter question: what if the exceedingly high concentrations actually indicate that the signal is not biological in origin? Could there be an abiotic, non-living chemical pathway capable of efficiently producing dimethyl sulfide in hydrogen-rich atmospheres? Laboratory experiments have explored this very possibility. Scientists have successfully synthesized trace amounts of dimethyl sulfide by mixing methane and hydrogen sulfide and exposing them to ultraviolet radiation. However, trace amounts translate to parts per billion, not the parts per million observed. These experimental outcomes fall short by factors of thousands. How can a molecule with such a fleeting existence persist long enough to be detected? Every molecule possesses a finite lifespan, representing the average duration it remains intact before decomposing. For dimethyl sulfide within Earth's atmosphere, this lifespan is exceptionally short. One study documented an average lifespan of 24 hours, while another reported 48 hours. Variations in this figure are contingent upon localized conditions such as sunlight intensity, ambient temperature, and the prevalence of oxidizing chemicals. Nevertheless, the overarching conclusion remains consistent: dimethyl sulfide does not endure for extended periods. This is a well-established scientific fact, corroborated by numerous independent investigations. 3 primary mechanisms contribute to the destruction of dimethyl sulfide in Earth's atmosphere. Firstly, hydroxyl radicals actively engage with it. These radicals are molecular fragments characterized by unpaired electrons, rendering them exceptionally reactive. They are formed when ultraviolet light causes water molecules in the upper atmosphere to dissociate. Once formed, hydroxyl radicals readily attack nearly any organic molecule they encounter. They abstract hydrogen atoms, thereby breaking chemical bonds. Dimethyl sulfide possesses 6 hydrogen atoms that are prime targets for this process. Secondly, oxygen directly reacts with dimethyl sulfide. While this reaction proceeds at a slower rate than interactions with hydroxyl radicals, it remains significant. Oxygen initially combines with the sulfur atom, producing sulfur dioxide as an intermediate product. Ultimately, this pathway leads to the formation of sulfuric acid. This is precisely why the combustion of sulfur-containing fossil fuels results in acid rain. The sulfur transforms into sulfur dioxide, then sulfuric acid, which precipitates back to Earth. The same chemical processes occur naturally with dimethyl sulfide in the atmosphere. Thirdly, sunlight itself can induce the fragmentation of dimethyl sulfide. Photodissociation occurs when a photon possesses sufficient energy to rupture chemical bonds. For dimethyl sulfide, ultraviolet wavelengths ranging between 200 and 300 nanometers carry the necessary energy to break the carbon-sulfur bonds that hold the molecule together. The resulting fragments then recombine with other atmospheric constituents. Now, let us consider a hydrogen-dominated atmosphere. Hydroxyl radicals still form, but their generation is less efficient. Hydrogen atmospheres contain a reduced amount of water vapor available for dissociation. A diminished supply of water vapor translates to fewer hydroxyl radicals. Fewer radicals, in turn, lead to a slower rate of dimethyl sulfide destruction. Models indicate that the concentration of hydroxyl radicals in the atmosphere of this ocean world might be 1/10 or even 1/100th of Earth's levels. Oxygen presents even more pronounced differences. This ocean world contains negligible amounts of oxygen. Spectroscopic observations reveal no discernible oxygen signatures. Consequently, the direct oxidation pathway that efficiently degrades dimethyl sulfide on Earth is largely inoperative there. The elimination of a major destruction route inherently extends the molecule's atmospheric persistence. Photodissociation still occurs. The planet's star emits ultraviolet radiation, although red dwarfs typically produce less UV light than our Sun. The hydrogen atmosphere itself may absorb some UV radiation before it reaches lower altitudes, where dimethyl sulfide is concentrated. Methane and carbon dioxide also absorb certain UV wavelengths, providing an additional layer of shielding. The net outcome is that dimethyl sulfide experiences less photochemical stress. When all these factors are considered collectively, dimethyl sulfide might endure 10 times longer, and potentially even 100 times longer, than it does on Earth. Instead of persisting for 1 or 2 days, it could remain intact for weeks or months. This significantly alters the production requirements. If replenishment is only needed every few weeks rather than daily, considerably less biological activity is necessary to maintain the same atmospheric concentration. A 10-fold increase in atmospheric lifetime reduces the production demands by a factor of 10. However, here lies the critical caveat. Even with a 100-fold increase in its lifespan, a substantial production rate is still required to sustain a concentration of 10 parts per million. The mathematical reality remains unavoidable. Something on this world is generating dimethyl sulfide at rates that dwarf anything observed on Earth. The extended atmospheric lifetime assists in explaining how the concentration can remain so elevated, but it does not negate the necessity of a potent source. Scientists are actively engaged in refining estimates of the molecule's atmospheric lifetime through sophisticated atmospheric modeling. They input the observed concentrations of methane, carbon dioxide, and hydrogen. They meticulously calculate the photochemistry, reaction by reaction, tracking the interactions between all constituent molecules. They estimate the ultraviolet flux emitted by the star. They model temperature and pressure at various atmospheric altitudes. The result is a predicted lifespan for dimethyl sulfide under those specific environmental conditions. Initial models suggest lifetimes ranging between 10 and 100 days, although substantial uncertainty persists. Could there be an explanation for these observed signals that entirely excludes the possibility of life? Not all scientists are convinced that the dimethyl sulfide signal definitively points to the presence of life. A growing contingent of researchers advocates for an alternative hypothesis. What if this celestial body entirely lacks oceans? What if its surface is composed of molten rock encased within a hydrogen atmosphere? Magma oceans, it is argued, could potentially generate chemical signatures that are indistinguishable from those produced by living oceans. This alternative explanation stems from detailed climate modeling published in early 2024. Here's how magma oceans might operate. The planet receives a significant amount of starlight, despite orbiting a faint red dwarf star. A dense hydrogen atmosphere creates a powerful greenhouse effect. While hydrogen is not as efficient as carbon dioxide at trapping heat, a substantial quantity can induce considerable warming. Models predict that surface temperatures could exceed 800 degrees Celsius under these conditions. This is a theoretical projection based on energy balance calculations and established atmospheric properties. At such extreme temperatures, rock undergoes melting. Granite typically melts around 1200 degrees Celsius, and basalt around 1100 degrees Celsius. However, rocks are complex mixtures of minerals, and some constituent minerals melt at lower temperatures. A planetary surface experiencing temperatures of 800 degrees Celsius would not be entirely molten, but it could feature extensive lava flows, molten lakes, and regions of liquid rock covering significant portions of its surface. Imagine the volcanic moon Io, orbiting Jupiter, but scaled up to 2.5 times the size of Earth. Magma interacts with planetary atmospheres in intricate ways. Volcanic gases are released through bubbling processes within the molten rock. These gases encompass water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. When hydrogen sulfide enters a hydrogen-rich atmosphere, chemical reactions ensue. At elevated temperatures, hydrogen sulfide can react with carbon-containing molecules to form organic sulfur compounds. Laboratory experiments have successfully demonstrated this phenomenon. However, the yields produced are typically low. Continuous volcanic outgassing, on the other hand, could sustain a steady rate of production. One research team meticulously calculated the relevant parameters. They modeled a planet with a molten surface, a hydrogen atmosphere, and volcanic outgassing rates comparable to Earth's most active volcanic periods. Their models successfully generated dimethyl sulfide through abiotic chemical processes. However, the resulting concentrations fell short by factors of 10 to 100 when compared to observational data. While they could produce dimethyl sulfide without invoking life, the quantity was insufficient. This discrepancy suggests that biological processes might still be necessary, but it does not definitively rule out the possibility of enhanced volcanic processes that are not yet fully understood. There is another significant clue: ammonia. On Earth, atmospheres rich in nitrogen produce ammonia when lightning or other energy sources facilitate the combination of nitrogen with hydrogen. Ammonia is also a product of biological activity. Numerous bacterial species generate ammonia as a metabolic waste product. Models predict that a habitable ocean world should exhibit detectable levels of ammonia. However, observational data reveals a complete absence of this molecule. The lack of ammonia is a rigorously confirmed finding, established through spectroscopic analysis. Magma ocean models offer a natural explanation for this missing ammonia. Nitrogen possesses the property of dissolving into molten rock under conditions of high pressure. This phenomenon is technically referred to as nitrogen partitioning into the melt phase. If the planet's surface is molten, atmospheric nitrogen is absorbed into the magma. This process effectively depletes the atmosphere of ammonia. The result is a planet where nitrogen is sequestered within the surface rather than existing as a gas in the atmosphere. This scenario aligns perfectly with the observed data. Ocean world models, conversely, encounter difficulties in explaining the absence of ammonia. If liquid water is present at the surface, nitrogen should remain in the atmosphere. Ammonia should form through both chemical reactions and biological processes. Its absence, therefore, presents a perplexing enigma for these models. Some scientists propose that certain metabolic pathways within life forms could consume ammonia as rapidly as it is produced. However, this requires very specific and potentially unusual environmental conditions. The magma ocean explanation, by contrast, is considerably more straightforward. It does not necessitate any specialized biological mechanisms, relying solely on fundamental chemical principles. Yet, magma ocean models are not without their own challenges. They struggle to account for the methane detected in the atmosphere. Methane is inherently unstable at high temperatures. It decomposes into carbon and hydrogen at temperatures exceeding approximately 700 degrees Celsius. To maintain atmospheric methane concentrations of 1% would necessitate either continuous production or cooler surface temperatures than magma ocean models predict. Either of these possibilities presents a significant hurdle for the magma ocean hypothesis. The scientific debate on this matter continues. Some researchers lean towards the magma ocean explanation due to its ability to account for the missing ammonia. Others favor the ocean world hypothesis because it provides a more coherent explanation for the abundant methane and the presence of dimethyl sulfide. Both factions agree that further observations are imperative. Subsequent observational campaigns utilizing advanced telescopes may detect other molecular compounds that could definitively resolve the question. Certain chemicals are expected to exist exclusively under magma conditions, while others would be indicative of the presence of liquid water. What if the planet does indeed possess water, but its atmosphere is far more alien than initially conceived? Hydrogen overwhelmingly dominates this planet's atmosphere. Spectroscopic observations provide conclusive evidence for this composition. The absorption features, which describe how starlight is filtered by the atmosphere, all strongly indicate the presence of vast quantities of hydrogen and helium. This presents a fundamental obstacle for life as we currently understand it. Earth's atmosphere comprises 78% nitrogen, 21% oxygen, and only trace amounts of other gases. There is virtually no free hydrogen at ground level. Hydrogen, being exceptionally light, readily escapes Earth's gravitational pull and dissipates into space. However, this ocean world is considerably more massive. Its substantial gravitational pull anchors hydrogen. Terrestrial life originated within an environment rich in nitrogen and oxygen. Our proteins, enzymes, and the very machinery of our cells are predicated upon specific atmospheric chemical conditions. Oxygen functions as the ultimate electron acceptor during respiration, the process that fuels the majority of complex life forms. Without oxygen, organisms are confined to anaerobic metabolism, which suffices for bacteria and simpler entities, but complex multicellular beings capable of constructing civilizations require oxygen or an analogous alternative. A hydrogen-dominated atmosphere fundamentally alters this equation. Unlike the inert nature of nitrogen, hydrogen actively participates in chemical reactions, reducing other molecules, the inverse of oxidation. This influences the feasibility of various chemical processes. Reactions readily occurring in oxygen-abundant atmospheres become challenging or impossible in hydrogen-rich ones, while entirely new reactions become favorable. Remarkably, life might not merely tolerate hydrogen atmospheres, but could potentially flourish in them. Recent laboratory investigations into the survival of Earth microbes in pure hydrogen yielded startling results. Bacteria and yeast, which typically do not encounter significant amounts of hydrogen, thrived when exposed to atmospheres composed entirely of hydrogen. This constitutes experimentally validated data, published in scholarly journals. While the organisms did not exhibit accelerated growth, they also did not perish, indicating a capacity for adaptation. Hydrogen presents metabolic opportunities. Certain terrestrial bacteria utilize hydrogen as an energy source, synthesizing methane by combining it with carbon dioxide and deriving energy from this process. These methanogens inhabit environments ranging from deep-sea hydrothermal vents to swamps and the digestive tracts of animals, demonstrating the viability of hydrogen-based metabolism. On a planet abundant in atmospheric hydrogen, these metabolic pathways could become predominant. The critical question then arises: could complex organisms evolve in such settings? On Earth, the transition from single-cell to multicellular life coincided with a rise in oxygen levels. The Great Oxidation Event, occurring 2.4 billion years ago, saturated our atmosphere with oxygen produced by photosynthetic bacteria. Within a few 100 million years, complex life emerged. While correlation does not definitively prove causation, the temporal proximity is compelling. Some scientists posit that oxygen's high energy density makes it ideal for powering complex life. Others contend that any sufficiently energetic metabolic process could suffice. Hydrogen metabolism yields less energy per reaction than oxygen metabolism, but it still provides energy. It is possible that complex life evolves at a slower pace in hydrogen-rich atmospheres, or perhaps it adopts different forms, or potentially remains confined to microbial communities. Our limited sample size of one example of life prevents definitive conclusions. The hydrogen atmosphere on this ocean world likely originated from the planet's formation. During planetary accretion, gas is gathered from the surrounding nebula. Larger planets capture more gas. If a planet grows sufficiently massive at a rapid rate, it can accumulate vast quantities of hydrogen and helium before stellar radiation disperses the nebula. This ocean world likely acquired several Earth masses of hydrogen during its formation, a theoretical concept well supported by planetary formation models. Over time, atmospheric escape gradually diminishes the hydrogen content. High-energy particles emanating from the star dislodge hydrogen atoms from the upper atmosphere, imparting sufficient velocity to overcome the planet's gravitational pull and drift away. Red dwarf stars, with their frequent flares, can accelerate this process. Nevertheless, this world has retained its hydrogen atmosphere for billions of years, suggesting either its youth or a substantial atmospheric thickness capable of withstanding such losses. Atmospheric thickness is crucial for habitability. A tenuous hydrogen atmosphere would retain minimal heat, whereas a dense one would induce extreme greenhouse warming. The challenge lies in achieving a delicate equilibrium. Too thin, and any liquid water would freeze. Too thick, and surface pressures would become crushing. Models indicate this planet resides near the edge of the habitable zone, where minor alterations in atmospheric mass could render it either habitable or uninhabitable. Some scientists perceive this world as bearing a greater resemblance to Neptune than to Earth. Neptune possesses a radius approximately 4 times that of Earth and a mass 17 times greater. Its atmosphere is predominantly hydrogen and helium, with roughly 2% methane. Beneath this atmospheric layer lies a mantle composed of water, ammonia, and methane ices, with a rocky core, perhaps slightly larger than Earth, situated even deeper. Neptune is not a gas giant like Jupiter, but an ice giant, characterized by volatile compounds rather than solely hydrogen gas. Despite its smaller size, this ocean world shares numerous characteristics with Neptune. Its density provides some insight. Neptune's density is 1.6 grams per cubic centimeter, while this ocean world measures 2.67 grams per cubic centimeter. For comparison, Earth's density is 5.5 grams per cubic centimeter. The progression in density is evident, placing this planet between Neptune and Earth. Simple calculations suggest it contains less rock than Earth and more rock than Neptune. The intervening composition remains to be determined. Interior structure models offer potential answers. Scientists input the observed mass and radius and incorporate constraints from planetary science. Rocky materials possess specific densities. Water ice under pressure exhibits a different density, and compressed hydrogen gas has yet another density. By examining various combinations, scientists can delineate plausible interior structures, a theoretical process grounded in established physics and chemistry derived from laboratory experiments and quantum mechanics. Most models converge on a similar depiction: a rocky core ranging from 1 to 3 Earth masses, overlaid by a substantial mantle of high-pressure ice and potentially liquid water, possibly measuring 1,000 to 2,000 meters in thickness. Above this lies a hydrogen-helium atmosphere extending for thousands of miles, gradually thinning with increasing altitude. This structure bears no resemblance to Earth's and appears more akin to a diminutive Neptune, with slightly more rocky material and less gas. If this model is accurate, the planet lacks a solid surface in any conventional sense. Descending through the atmosphere would reveal progressively higher pressures and temperatures. Eventually, the hydrogen would become dense enough to behave as a liquid. Deeper still, the icy mantle would begin. However, there would be no distinct boundary, no specific point at which a spacecraft could land. The transition from atmosphere to ice would occur gradually over hundreds of miles, mirroring the structure of Neptune. Observations suggest this ocean world functions similarly, yet this interpretation contradicts the detection of dimethyl sulfide. Neptune does not produce dimethyl sulfide. Its atmosphere contains methane, ethane, acetylene, and other hydrocarbons, with no sulfur-based organic molecules ever detected. If this distant world resembles Neptune, why does it exhibit a chemistry absent in Neptune? One plausible explanation involves a layer of liquid water situated between the ice mantle and the hydrogen atmosphere. At specific depths, pressure and temperature conditions could permit liquid water to exist. This water would not be in direct contact with space or the atmosphere, as Earth's oceans are, but would be confined beneath thousands of miles of hydrogen. Nevertheless, it could potentially support life. Microbes suspended within this subterranean ocean could generate dimethyl sulfide, which would then bubble up through the atmosphere, reaching altitudes detectable by telescopes. Critics, however, raise concerns regarding this scenario. How would life originate in a buried ocean? On Earth, life likely began in shallow pools or near hydrothermal vents, environments where energy and chemicals concentrate. A buried ocean would lack these features, exhibiting scarce energy and limited nutrients, rendering the initiation of life implausible. Yet, if life were to somehow commence through an unknown mechanism, it might then propagate and flourish. Another point of contention is methane. Neptune contains 2% methane, whereas this ocean world has only 1%. On Neptune, methane originates from the planet's interior, released through convection and atmospheric mixing. If this world mirrors Neptune, its methane might share the same source. However, ocean world models propose a different origin: biological production, with methanogens creating methane from hydrogen and carbon dioxide. Both hypotheses align with the observational data, making it difficult to definitively distinguish between them. The central debate revolves around whether this planet possesses a surface and oceans or is devoid of both. Spectroscopy reveals the atmospheric chemical composition, but does not directly ascertain subsurface conditions. Surface characteristics are inferred from atmospheric composition, but these inferences can be erroneous, as multiple explanations can account for the same data. Further observations that probe deeper into the planet's nature are required to resolve this ambiguity. What occurs when scientists investigate the perplexing absence of a critical atmospheric component? The concept of Hycean worlds emerged in 2021 from theoretical research conducted at Cambridge. The researchers posed a straightforward question: could planets larger than Earth, but smaller than Neptune, sustain liquid water oceans despite possessing hydrogen atmospheres? Conventional scientific understanding suggested this was impossible, as hydrogen atmospheres were believed to induce runaway greenhouse effects, rendering surfaces excessively hot. However, detailed modeling revealed a different possibility, a theoretical framework based on established climate physics. The pivotal factor is cloud formation. High in the atmosphere, water vapor can condense into clouds, reflecting stellar radiation back into space before it reaches and heats the surface. If sufficient cloud cover develops, it could maintain a cool planetary surface, even with a significant greenhouse effect lower down. An optimal balance is achieved when cloud cover ranges from approximately 50 to 70% of the planet. Insufficient cloud cover leads to surface overheating, while excessive cloud cover prevents starlight from penetrating sufficiently to support photosynthesis or warm the water. Hycean worlds would experience surface pressures between 100 and 1,000 times Earth's atmospheric pressure. While this sounds extreme, Earth's oceans already encounter such pressures just a few miles below the surface, and life thrives in the deep ocean despite pressures exceeding 1,000 times surface levels. If life can adapt to these pressures in Earth's oceans, it might similarly adapt to those found on a Hycean surface, where the pressure originates from the atmosphere rather than water depth. Temperature presents a more intricate constraint. At Earth's surface pressure, water remains liquid between 0 and 100 degrees Celsius. However, at elevated pressures, water maintains its liquid state at higher temperatures. At 100 atmospheres of pressure, water boils at 311 degrees Celsius instead of 100. At 200 atmospheres, the boiling point rises to 365 degrees Celsius, a phenomenon confirmed by laboratory pressure-temperature phase diagrams for water. The upper limit is reached at the critical point of water, above 374 degrees Celsius and 221 atmospheres, where water transitions into a supercritical state, a phase where liquid and gas merge. Supercritical water possesses unusual properties. It flows like a gas yet dissolves substances like a liquid. While it might potentially support life, life as we understand it depends on the distinct characteristics of liquid water. Transitioning to a supercritical state could render habitability impossible. Hycean models suggest that surface temperatures between 10 and 70 degrees Celsius are achievable under specific conditions, a range compatible with life. Earth's most extreme environments, such as deep-sea hydrothermal vents, reach temperatures exceeding 100 degrees Celsius and harbor thriving bacterial communities. If Hycean oceans remain cooler than this, life appears plausible. However, establishing these temperatures necessitates a precise calibration of greenhouse warming and cloud cooling. The hydrogen atmosphere serves multiple functions. It provides greenhouse warming to prevent freezing, shields against harmful stellar radiation, and offers metabolic fuel for hydrogen-utilizing organisms. Conversely, it impedes ultraviolet light, which drives photosynthesis on Earth. Hycean life might need to adapt to dimmer, redder light that penetrates the atmosphere, though this may not be a significant impediment given that red dwarf stars primarily emit red and infrared light. Nutrient availability poses another challenge. On Earth, continental weathering releases minerals into rivers that flow into oceans, providing essential nutrients for marine life. Hycean worlds may lack continents altogether, precluding weathering. Nutrients might be supplied to the ocean through volcanic activity on the seafloor, releasing minerals directly into the water, or through chemicals seeping up from the rocky mantle beneath. One intriguing prediction is that Hycean worlds should exhibit specific atmospheric signatures: elevated methane levels due to biological production, high carbon dioxide from volcanic outgassing or biological respiration, detectable water vapor, and potentially biosignature gases such as dimethyl sulfide or methyl chloride. This ocean world aligns almost perfectly with the predicted pattern, and the congruence between prediction and observation is a source of considerable excitement among researchers. How do thick atmospheres contribute to stable conditions? Greenhouse effects often acquire a negative reputation, with discussions of climate change frequently highlighting runaway greenhouse warming as catastrophic. However, greenhouse effects are not inherently detrimental. They are fundamental to Earth's habitability. Without our natural greenhouse effect, Earth's average temperature would be -8 degrees Celsius, leading to completely frozen oceans. Instead, greenhouse gases maintain a comfortable average of +15 degrees Celsius. This is a fundamental principle of atmospheric physics, substantiated by decades of measurements. The mechanism is straightforward. Sunlight passes through the atmosphere, warming the surface. The heated surface then radiates energy back as infrared light. Greenhouse gases absorb this infrared radiation, trapping heat in the lower atmosphere. These gases eventually re-emit the energy, with a portion directed back towards the surface, resulting in a warming effect. Increased greenhouse gas concentrations lead to greater warming, a relationship that, while not linear, is predictable. On Earth, carbon dioxide and water vapor are the primary contributors to the greenhouse effect, with methane and nitrous oxide playing smaller roles. These gases function because their molecular structures absorb specific infrared wavelengths. Not all gases possess this capability. Nitrogen and oxygen, which constitute the bulk of our atmosphere, are transparent to infrared radiation and do not contribute to greenhouse warming. Hydrogen and helium are similarly transparent, necessitating the presence of other molecules. While this ocean world's hydrogen atmosphere does not directly trap much heat, it contains approximately 1% methane and 1% carbon dioxide. Although these proportions may seem minor, they are sufficient. Earth's atmosphere contains only 400 parts per million of carbon dioxide, equivalent to 0.04%. This distant planet possesses 25 times more carbon dioxide than Earth. Methane is an even more potent greenhouse gas than carbon dioxide, molecule for molecule. 1% methane provides substantial warming. This is where hydrogen becomes significant. The sheer mass of the hydrogen atmosphere increases surface pressure, resulting in denser air. Denser air retains more heat, and also impedes the escape of infrared radiation. Photons attempting to exit the planet are absorbed and re-emitted multiple times before finally reaching space, with each absorption-emission cycle delaying heat loss. Consequently, even though hydrogen itself is not an efficient infrared absorber, a substantial hydrogen atmosphere still induces considerable greenhouse warming solely through pressure effects. Models demonstrate that a hydrogen atmosphere containing 1% carbon dioxide and 1% methane can maintain surface temperatures sufficiently warm for liquid water, even on planets receiving less stellar radiation than Earth. This effectively extends the habitable zone outward from the star, rendering planets that would otherwise be too cold with Earth-like atmospheres warm enough with hydrogen atmospheres, thereby challenging conventional perspectives on where to search for life. However, there is a caveat. The greenhouse effect must be strong but not excessively so. Venus serves as a stark example of runaway greenhouse warming. Venus receives twice the sunlight of Earth and possesses a crushing carbon dioxide atmosphere, leading to surface temperatures of 470 degrees Celsius, hot enough to melt lead. The greenhouse effect spiraled out of control. All water evaporated, generating more greenhouse gas, which intensified warming, leading to further evaporation, a self-reinforcing cycle with no breaking mechanism. This ocean world hovers precariously on the edge. Computer simulations indicate that minor variations in atmospheric composition or cloud cover could propel it into a runaway greenhouse state. If clouds fail to form, surface temperatures would surge, causing water to evaporate and generating additional greenhouse warming. Once initiated, this process might be irreversible. Conversely, if cloud cover becomes excessively dense, it would block too much starlight, causing surface temperatures to plummet, leading to water freezing. Frozen surfaces would reflect more light, inducing further cooling, another runaway process, albeit in the opposite direction. The apparent stability of conditions on this planet suggests a regulatory mechanism. It is possible that biological processes contribute to climate stabilization. On Earth, phytoplankton produce dimethyl sulfide, which acts as cloud condensation nuclei. Increased warming stimulates phytoplankton growth, leading to greater dimethyl sulfide production, which in turn promotes cloud formation and consequently induces cooling. This negative feedback loop may prevent runaway warming, and a similar mechanism could operate on this ocean world. If so, life would not merely exist there, but would actively regulate the planet's climate, thereby ensuring its habitability. Why does the absence of ammonia divide scientific opinion? Ammonia should be present, as predicted by multiple models, yet observations show no trace. This absence has become a focal point of debate regarding the planet's atmosphere. Ammonia is a compound of nitrogen and hydrogen, with a chemical formula NH3, consisting of one nitrogen atom bonded to 3 hydrogen atoms. In a hydrogen-rich atmosphere energized by starlight or lightning, ammonia formation is expected. This is a chemically validated phenomenon observed in laboratory experiments and in the atmospheres of gas giants within our solar system. Jupiter, Saturn, Uranus, and Neptune all contain ammonia, wherever hydrogen and nitrogen are present with sufficient energy to drive reactions. Spectroscopic analysis of these planets reveal distinct ammonia absorption features, leaving no doubt about its presence. The puzzle lies in its absence on this ocean world, despite its expected presence. One proposed explanation involves biological consumption. Certain terrestrial bacteria metabolize ammonia as an energy source, with nitrifying bacteria converting ammonia first to nitrite and then to nitrate, deriving energy from these transformations. In an ocean teeming with such bacteria, ammonia could be removed from the atmosphere as rapidly as it forms, with the ocean acting as a sink. Atmospheric ammonia would dissolve into the water, be consumed by bacteria, and more atmospheric ammonia would dissolve to replenish the depleted amount, establishing an equilibrium where ammonia concentrations remain near zero. This explanation aligns well with the Hycean world hypothesis, as it necessitates the presence of life, which is already suggested by the dimethyl sulfide signal. Indeed, these two pieces of evidence mutually support each other. Biological metabolism accounts for both the presence of dimethyl sulfide and the absence of ammonia, creating a self-consistent picture. However, this relies on the assumption of life's existence, precisely what scientists are endeavoring to prove, raising the risk of circular reasoning. An alternative explanation invokes abiotic chemistry. If the surface were molten rock, nitrogen would dissolve into the magma. Experimental studies of volcanic systems demonstrate that under conditions of high temperature and pressure, nitrogen preferentially partitions into melt phases rather than remaining in the gaseous state. A magma ocean would effectively sequester atmospheric nitrogen, thereby preventing ammonia formation. The absence of ammonia would then serve as evidence for a magma ocean rather than a water ocean. This explanation neatly fits the magma ocean hypothesis, requiring no life and explaining the missing ammonia through straightforward chemical principles. However, it struggles to account for the dimethyl sulfide detection. As previously discussed, magma ocean models can produce trace amounts of dimethyl sulfide through abiotic chemical processes. it remains uncertain if they can generate sufficient quantities. The prevailing magma ocean hypothesis effectively resolves one enigma while simultaneously presenting another. A less frequently considered third scenario exists. It is possible that the spectroscopic analysis simply overlooked the presence of ammonia. Ammonia exhibits distinct absorption patterns at specific light wavelengths. If these particular wavelengths were not subjected to observation, or if background noise masked the signal, ammonia could have been present but remained undetected. However, the James Webb Space Telescope meticulously scanned numerous wavelength ranges. Its instruments possess the requisite sensitivity to identify ammonia at anticipated concentrations. Independent analyses were conducted by multiple scientific teams, all converging on the identical conclusion: no ammonia detected. The absence of detectable ammonia compels scientists to make a choice between competing hypotheses. They must either accept that life is consuming it, that magma is absorbing it, or that some other, as yet undiscovered process is responsible for its removal. Each of these possibilities charts a distinct course for our comprehension of this celestial body. We are left to ponder an ocean world teeming with life, a molten ocean devoid of it, or a reality entirely beyond our current expectations. The scientific community remains divided. A significant contingent of researchers staunchly champions the biological explanation. Others are more inclined towards the magma ocean theory. A third faction contends that the existing data is too equivocal to permit a definitive choice. All parties, however, concur that further observations are urgently required to surmount this impasse. Envision an ocean where every single droplet of water harbors 1,000 times the microbial density of Earth's most flourishing seas. This is precisely what the numerical data implies. The observed concentrations of dimethyl sulfide necessitate an extraordinary level of biological activity. On our planet, phytoplankton, microscopic marine algae, inhabit the sunlit upper layers, extending down to approximately 600 feet where light penetrates. Below this stratum, perpetual darkness prevails, and photosynthesis ceases. On this distant ocean world, the same depth limitation would likely apply, absent any factors that alter these fundamental principles. One conceivable factor is simply density. Earth's oceans contain, on average, about 1 million bacterial cells per milliliter of seawater. While this sounds substantial, consider that fertile soil boasts 1 billion cells per gram. Seawater, in comparison to other environments, is relatively dilute in microbial life. It is plausible that this remote ocean environment is analogous to fertile soil. Imagine dense bacterial mats suspended within the water column, or thick biofilms encrusting every available surface. Such a scenario would imply a microbial density 1,000 times greater than that found in Earth's oceans, a premise strongly supported by the mathematical requirements. Another potential explanation involves entirely different organisms. On Earth, dimethyl sulfide is predominantly produced by eukaryotic phytoplankton, organisms characterized by complex cells containing nuclei and organelles. These evolved relatively late in Earth's history, approximately 2 billion years ago. Prior to their emergence, simpler bacteria were the dominant life forms. It is conceivable that this ocean world harbors bacteria that generate dimethyl sulfide through alternative metabolic pathways. Bacteria possess a remarkable capacity for rapid evolution, adapting to local conditions within mere thousands of generations. An ocean teeming with dimethyl sulfide producing bacteria could readily account for the observed concentrations. The presence of a hydrogen-rich atmosphere opens up unique metabolic avenues. Certain Earth-dwelling bacteria, known as methanogens, synthesize methane by combining hydrogen gas with carbon dioxide, thereby deriving energy from this reaction. This process is highly effective in oxygen-deprived environments. It is plausible that analogous organisms on this ocean world might directly produce dimethyl sulfide by combining hydrogen with sulfur compounds. This direct synthesis would represent a more efficient process than Earth's typical pathway, where dimethyl sulfide arises as a secondary byproduct rather than a primary metabolic product. Temperature also plays a crucial role. Warmer water accelerates metabolic rates. Chemical reactions, in general, roughly double in speed with every 10 degrees Celsius increase in temperature. If the average surface temperature of this ocean is 30 degrees Celsius, compared to Earth's average of 4 degrees Celsius, reactions would proceed approximately 8 times faster. An 8-fold increase in metabolic speed translates directly to an 8-fold greater production of dimethyl sulfide per cell. Multiplying this elevated cellular output by a higher cell density readily brings us closer to the required production rates. Furthermore, the concept of evolutionary pressure warrants consideration. On Earth, phytoplankton produce dimethylsulfonneopropionate to regulate their salt balance, with dimethyl sulfide being an incidental byproduct. However, what if the organisms inhabiting this world utilize dimethyl sulfide for communication? Bacteria on Earth employ chemical signals to coordinate their activities, a phenomenon termed quorum sensing. When a sufficient population of bacteria congregates in a particular location, their emitted chemical signals reach a critical concentration, triggering coordinated collective behaviors. It is conceivable that dimethyl sulfide serves a similar signaling function in this environment, with organisms deliberately producing it in substantial quantities for this purpose. On Earth, energy availability is a fundamental driver of biological productivity. Photosynthesis harnesses solar energy, converting it into chemical energy that sustains the food web. This distant ocean world receives a comparable amount of stellar radiation to Earth. Its parent star, a red dwarf, emits a spectrum richer in red and infrared light than our Sun's broader range. Nevertheless, certain Earth organisms are highly efficient at photosynthesizing using red light. For instance, purple bacteria and some cyanobacteria flourish in environments dominated by red light. It is highly probable that life on this alien world has undergone similar adaptations. Nutrient availability is an equally critical factor on Earth. Upwelling currents bring nutrient-rich water from the deep ocean to the surface, fostering highly productive regions such as the coast of California and the waters surrounding Antarctica. In the absence of continents to generate coastal upwelling, this ocean world might depend on alternative mechanisms for nutrient distribution. It is possible that nutrients are released directly into the water column from subsurface sources. Alternatively, intense tidal forces exerted by the nearby star could induce mixing, bringing deep-sea nutrients to the surface. Regardless of the specific mechanism, high biological productivity invariably necessitates a substantial supply of nutrients. But can life even withstand the significant temperature fluctuations experienced on this planet? Life on Earth demonstrably endures an astonishing array of extreme conditions. Bacteria thrive in the scalding waters of hot springs, reaching temperatures as high as 90 degrees Celsius. Other organisms survive in Antarctic ice at temperatures as low as -40 degrees Celsius. Tardigrades, microscopic invertebrates colloquially known as water bears, are capable of withstanding temperatures ranging from near absolute zero to 150 degrees Celsius. Life, in essence, is far more resilient than commonly perceived. These extreme survival capabilities are substantiated by direct observation and rigorous laboratory testing. However, this particular ocean world might present challenges that surpass even Earth's recorded extremes. Climate modeling indicates that, contingent upon atmospheric conditions, surface temperatures could fluctuate dramatically, ranging from 10 degrees Celsius to over 70 degrees Celsius. The planet's elliptical orbit contributes to these variations throughout its 33-day year. Temperatures surge when the planet is closest to its star and plummet when it is farthest away. The difference between these orbital extremes could easily exceed 20 degrees Celsius. Any life forms present must either adapt to these dramatic temperature swings or discover strategies to evade them. Terrestrial organisms employ a variety of survival tactics for temperature tolerance. Some enter a dormant state during unfavorable conditions. Bacterial spores, for example, can persist for thousands of years in a state of suspended animation, awaiting improved environmental circumstances. Upon the return of favorable temperatures, they reactivate and resume their growth. It is plausible that organisms on this ocean world enter a similar spore-forming state during temperature extremes, subsequently blooming during periods of moderate temperatures. This cyclical pattern of biological activity would align with the planet's orbital cycle. Other organisms utilize biochemical adaptations. Proteins, essential for cellular function, achieve their specific shapes through a folding process. Temperature significantly impacts protein stability. Excessive heat causes proteins to unfold and lose functionality, while extreme cold slows down enzyme activity. However, thermophilic organisms, or heat-loving bacteria, produce proteins with additional chemical bonds that enhance structural stability at elevated temperatures. Conversely, psychrophilic organisms, or cold-loving bacteria, possess flexible proteins that maintain activity even in frigid conditions. Life on this ocean world might combine both strategies, developing proteins capable of stable function across a broad spectrum of temperatures. The ocean itself provides a crucial buffering effect. Water possesses a high heat capacity, meaning it requires a considerable amount of energy to alter its temperature. Large bodies of water warm and cool gradually. Even with drastic fluctuations in air temperature, ocean temperatures remain comparatively stable. Earth's oceans typically exhibit diurnal temperature variations of merely 1 or 2 degrees Celsius at the surface, despite air temperature swings of 10 or 20 degrees Celsius. Similarly, an ocean on this distant world would effectively buffer temperature changes, mitigating the impact of orbital variations. Depth offers another sanctuary. On Earth, surface waters experience temperature fluctuations dictated by seasons and weather patterns. Deeper ocean layers, however, maintain stable temperatures year-round. Below approximately 600 feet, ocean temperatures show minimal change, typically remaining around 4 degrees Celsius in most locations, irrespective of surface conditions. Life could potentially retreat to these stable deepwater environments during periods of extreme surface temperatures, subsequently migrating to the more productive upper layers when conditions become favorable. Such vertical migration is a common behavior observed in Earth's oceans. Many organisms descend to deeper waters during the day and ascend at night. However, extreme temperatures introduce another significant challenge. Chemical reaction rates are intrinsically linked to temperature. This principle applies not only to biological reactions, but to all chemical processes. At higher temperatures, dimethyl sulfide degrades more rapidly. Conversely, at lower temperatures, it persists for longer durations. The variation in its atmospheric lifetime throughout the orbital cycle introduces complexity into climate modeling. Scientists must account for time-dependent chemistry, where reaction rates fluctuate as the planet traverses its elliptical orbit. There is evidence suggesting that life adapts more effectively to cyclical environmental extremes than to constant ones. Organisms can prepare for predictable changes. Prior to the onset of winter, trees mobilize nutrients into their root systems and shed their leaves. Before the arrival of the dry season, certain fish species bury themselves in mud and enter a state of hibernation. The key element here is predictability. If the 33-day orbital cycle repeats with consistent regularity, life could evolve adaptive responses triggered by environmental cues such as shifts in light intensity or temperature. However, temperature is not the sole obstacle presented by this planet. What of the issue of daylight, or rather the lack thereof? When a planet orbits exceptionally close to its star, The gravitational forces exerted by the star profoundly influence the planet's physical characteristics. The star's gravitational pull is significantly stronger on the side of the planet facing it than on the opposite side. This differential gravitational force, known as tidal force, generates internal friction within the planet. Over millions of years, this internal friction causes the planet's rotation to slow down. Eventually, the planet's rotational period synchronizes precisely with its orbital period, resulting in tidal locking. Consequently, one hemisphere permanently faces the star, bathed in perpetual daylight, while the other hemisphere is perpetually shrouded in darkness. This phenomenon is a well-established principle of physics, observable throughout our solar system. Our moon, for instance, is tidally locked to Earth, perpetually presenting the same face to us. Mercury is nearly tidally locked to the Sun, completing 3 rotations for every 2 orbits. It is highly probable that most planets orbiting close to red dwarf stars become fully tidally locked. The timescale for this process depends on factors such as the planet's distance from its star, its mass, and its internal structure. For this particular ocean world, orbiting a mere 13 million miles from its star, tidal locking likely occurred within the first few 100 million years of its existence. While theoretical, this conclusion is strongly supported by extensive calculations. Tidal locking precipitates dramatic consequences. The day side, exposed to constant stellar radiation, never experiences night, leading to persistently high temperatures. The night side, devoid of direct starlight, remains permanently frozen. Between these two extreme regions lies a twilight zone, a narrow band encircling the planet, where the star perpetually hovers at the horizon. This terminator region experiences neither full daylight nor complete darkness, potentially offering the only environment with moderate temperatures. On Earth, diurnal cycles profoundly influence weather patterns, ocean currents, and biological rhythms. Plants engage in photosynthesis during the day and respiration at night. Animals synchronize their activities with circadian rhythms. A tidally locked world fundamentally lacks these cyclical processes. Life on such a planet would need to adapt to constant environmental conditions, whether perpetual light or perpetual darkness. The twilight zone might harbor the most diverse array of life, benefiting from both illumination and temperate conditions. However, atmospheric circulation introduces a critical mitigating factor. A substantial atmosphere can effectively transport heat from the day side to the night side. On Earth, atmospheric circulation drives wind patterns, jet streams, and weather systems. On a tidally locked planet, this circulation would be far more pronounced. Air heated on the day side would ascend and flow towards the night side. Conversely, cold air on the night side would descend and move back towards the day side. The result is a planet-wide circulation cell characterized by winds potentially reaching hundreds of miles per hour. Computer simulations indicate that a thick hydrogen atmosphere could transport sufficient heat to prevent the night side from freezing entirely. While the day side might reach temperatures of 100 degrees Celsius or more, the night side could remain above freezing due to this heat transfer. This scenario creates habitable conditions across a significantly larger surface area than the twilight zone alone. The ocean itself would experience circulation patterns, driven by temperature gradients and wind stress. Warm water would flow from the day side towards the night side, with cold water returning via deep currents. Nevertheless, the perpetual illumination on the day side presents significant photochemical challenges. Sunlight drives chemical reactions within the atmosphere. On Earth, these reactions are largely reset each night when sunlight is no longer present. Reactive molecules produced during the day are broken down overnight, maintaining atmospheric balance. On a tidally locked planet, the day side experiences uninterrupted solar exposure. Photochemistry would proceed continuously, potentially degrading biosignature gases before they could disperse to the night side or alternatively, generating exotic chemical compounds unknown on Earth. The night side, conversely, poses its own set of challenges. Lacking any sunlight, photosynthesis is impossible. Any life forms existing on the night side would be compelled to rely on chemical energy sources rather than light. On Earth, deep-sea ecosystems found near hydrothermal vents provide compelling evidence that life can thrive independently of sunlight. Chemosynthetic bacteria derive energy from compounds such as hydrogen sulfide. An entire food web exists that is entirely decoupled from photosynthesis. It is conceivable that analogous ecosystems flourish across this planet's night side, sustained by chemicals brought to the surface through subsurface upwelling. Tidal locking also has implications for tidal forces themselves. With the planet perpetually presenting the same face to its star, the tidal bulges remain fixed in position. This would result in a permanent state of high tide on both the day side and night side, with permanent low tide occurring at the poles. This configuration would generate standing wave patterns distinct from anything observed on Earth. What if the entire interpretation leaning towards biological origins is incorrect? Scientists do not operate under the assumption that biology is the sole possible explanation. They rigorously investigate alternative hypotheses. Over the past decade, numerous research teams have explored the possibility of dimethyl sulfide formation occurring in the absence of life. Their findings have complicated the existing picture. In the year 2024, one research group published the results of experiments demonstrating that ultraviolet radiation can indeed catalyze reactions between methane and hydrogen sulfide, yielding small quantities of dimethyl sulfide. This represents validated experimental data, replicated under controlled laboratory conditions. The experimental methodology involved filling a sealed chamber with gas mixtures mimicking the potential atmospheric composition of exoplanets. These mixtures included hydrogen, methane, carbon dioxide, and hydrogen sulfide in various ratios. The chambers were then exposed to ultraviolet lamps calibrated to simulate stellar radiation. Over periods ranging from days to weeks, gas samples were periodically extracted and analyzed for their composition using mass spectrometry. The analyses revealed the formation of several organic sulfur compounds, including trace amounts of dimethyl sulfide. The underlying chemical mechanism involves free radicals, molecular fragments possessing unpaired electrons. Ultraviolet light induces the dissociation of methane molecules, generating methyl radicals. These highly reactive methyl radicals can then react with hydrogen sulfide, which itself undergoes dissociation under UV exposure. Through a complex series of intermediate reactions, methyl radicals combine with sulfur atoms to form dimethyl sulfide. While the chemistry is intricate, involving multiple sequential steps, the process is demonstrably viable. Therefore, dimethyl sulfide can indeed be produced abiotically. However, the yields observed in these experiments were minuscule. The produced dimethyl sulfide was detected at concentrations measured in parts per billion. To account for the observed parts per million levels on this ocean world would require yields thousands of times greater. The researchers themselves acknowledged this significant limitation. They posited that perhaps continuous volcanic outgassing of hydrogen sulfide, coupled with intense photochemistry, could potentially augment production. Yet, even under generous assumptions, these scenarios fell short of explaining the observed concentrations. Another experimental investigation explored alternative formation pathways. Scientists simulated conditions representative of molecular clouds, the cold, dense interstellar regions where stars originate. They mixed simple molecules onto ice grains and subjected them to radiation. Under these extreme extraterrestrial conditions, they successfully synthesized various organic compounds, including dimethyl sulfide. This experiment established that dimethyl sulfide can form in the vastness of space even before planets coalesce. It is conceivable that comets and asteroids could deliver dimethyl sulfide to planetary atmospheres through impact events. However, delivery via comets presents its own set of challenges. Any dimethyl sulfide introduced from space would likely be rapidly degraded by atmospheric chemistry. To maintain the observed atmospheric concentrations would necessitate continuous replenishment. This implies a planet subjected to constant bombardment by dimethyl sulfide-rich comets. Current observational data does not support such a scenario. Crater counts on planets and moons offer valuable insights into impact rates. Based on its estimated age and orbital characteristics, this ocean world is not expected to experience heavy bombardment. A third series of experiments focused on high-temperature chemistry. When hydrogen sulfide reacts with organic molecules at temperatures exceeding 500 degrees Celsius, a variety of sulfur compounds are generated. Submarine volcanic vents on the seafloor could potentially provide such high-temperature conditions. Hot fluids rich in hydrogen sulfide, mixing with organic molecules originating from either biological or abiotic sources, could lead to the formation of dimethyl sulfide. This pathway does not directly necessitate the presence of life, although it might rely on organic precursors that are ultimately produced by life. The primary challenge lies in the scale of these processes. While all these abiotic pathways are chemically plausible and have demonstrated measurable dimethyl sulfide production in laboratory settings, scaling them to planetary levels demands extraordinary conditions. These would include sustained intense ultraviolet radiation, exceptionally high rates of volcanic outgassing, and atmospheric composition specifically tailored to maximize production, while simultaneously minimizing degradation. The simultaneous occurrence of all these required factors seems improbable, though not strictly impossible. One researcher succinctly summarized the situation. Yes, we can produce dimethyl sulfide without life. But generating sufficient dimethyl sulfide to explain the observed data without invoking biology necessitates such a confluence of special conditions that invoking biological processes becomes the simpler explanation. Biological systems are inherently efficient at producing specific molecules. Abiotic chemistry, conversely, tends to produce a broad range of compounds simultaneously, albeit in smaller quantities. The observed specificity and abundance of dimethyl sulfide strongly point towards biological production. However, the possibility of spurious signals originating from space debris cannot be entirely discounted. In the year 2022, scientists reported a surprising discovery. They detected dimethyl sulfide on a comet. This comet, designated 67P/Churyumov-Gerasimenko, was extensively studied by the European Space Agency's Rosetta probe. Instruments aboard Rosetta meticulously sampled the gas and dust emanating from the comet's surface as it approached the Sun and warmed up. Among the dozens of molecules identified, dimethyl sulfide was present. This detection confirmed that dimethyl sulfide can indeed form through abiotic processes within cometary ice, predating the comet's own formation. This finding cast doubt on the definitive nature of dimethyl sulfide as a biosignature. If comets harbor dimethyl sulfide, its detection on a planet might not necessarily indicate the presence of life. It is plausible that impacts delivered the molecule to the planet's atmosphere. Alternatively, outgassing from deep within the planet could release cometary material that accreted during the planet's formation. Either of these scenarios could potentially explain the presence of atmospheric dimethyl sulfide without recourse to biological origins. This hypothesis is supported by direct observational evidence from comets, rather than mere speculation. However, the quantity of delivered material is a critical consideration. The dimethyl sulfide detected on the comet existed in very low concentrations, measured in parts per million within the cometary ice. When this ice sublimates into gas, its concentration further diminishes. To account for the atmospheric concentrations of 10 parts per million observed on this ocean world would necessitate an enormous number of cometary impacts. Scientists have calculated the requisite impact rate, and the numbers involved are staggering. It would require impacts delivering thousands of tons of cometary material into the atmosphere on a daily basis. Such an elevated impact rate would inevitably leave other detectable traces. Impacts deliver more than just dimethyl sulfide. Comets contain a complex mixture of substances, including water, carbon monoxide, ammonia, methanol, formaldehyde, and dozens of other molecules. If impacts were the source of dimethyl sulfide, they ought to be contributing all these other molecular compounds as well. However, atmospheric observations do not reveal any unusual concentrations of other cometary volatiles. Carbon monoxide appears to be absent or present in extremely low quantities. Ammonia is also missing. The observed chemical fingerprint does not align with the continuous influx of material from comets. There exists another complication: the speed of impact. When a comet collides with a planet, velocities typically range from tens to hundreds of kilometers per second. These hypervelocity impacts release immense amounts of energy, causing temperatures at the impact sites to soar to thousands of degrees. Under such extreme conditions, most molecules are obliterated. Complex organic molecules, such as dimethyl sulfide, would be broken down into simpler constituent fragments. Only the most resilient molecules are capable of surviving such an ordeal. Dimethyl sulfide, however, is not particularly robust. It should be destroyed rather than delivered intact. Some impacts do occur at reduced velocities. Should a planet gravitationally capture a comet, allowing it to spiral inward gradually, the impact velocity might be as low as a few kilometers per second. These gentler impacts could potentially preserve molecules more effectively, but such occurrences are infrequent. The majority of comets either miss the planet entirely or strike with significant force. The likelihood of experiencing continuous, low-velocity impacts over millions of years appears to be vanishingly small. There is one hypothetical scenario where cometary delivery might be plausible. If a planet formed in a region abounding with cometary material and incorporated vast quantities of it during its formation, that material could be stored within the planet's interior. Over extended periods, volcanic activity or internal convection might transport this material to the surface, releasing ancient cometary volatiles into the atmosphere. This scenario would not necessitate ongoing impacts, but rather the release of primordial material. Nevertheless, this hypothesis requires that the dimethyl sulfide survive within the planet's interior for billions of years. Planetary interiors reach temperatures of thousands of degrees, and pressures exceed millions of atmospheres. Under such extreme conditions, most molecules would degrade. Only the most chemically stable compounds would endure. Dimethyl sulfide would almost certainly be decomposed during this storage period. Water persists because of its exceptional stability. Simple gases like hydrogen, methane, and carbon dioxide also survive. Complex organic sulfur compounds, however, do not. The connection to comets remains a cautionary illustration rather than a viable explanation. It serves as a reminder to scientists that molecules considered biosignatures can originate from non-biological sources. It compels a more rigorous interpretation of observational data, but does not elucidate the specific case of this ocean world. The concentrations of dimethyl sulfide are excessively high. The complete absence of other cometary signatures is notable. The chemical environment is far too destructive to preserve delivered molecules over geological timescales. What about volcanic sources that mimic biological chemistry? Volcanoes on Earth emit sulfur in various forms. Sulfur dioxide is the predominant volcanic emission, released when magma ascends and the surrounding pressure decreases. Hydrogen sulfide, responsible for the characteristic rotten egg odor, is also released in volcanic regions. Sulfur's chemistry is intricate, with multiple oxidation states allowing it to form bonds with nearly any element. In volcanic settings, sulfur reacts with carbon, hydrogen, and oxygen to generate dozens of distinct compounds. This is a well-established geochemical process observed at volcanic sites globally. Could volcanic processes on this ocean world produce dimethyl sulfide? One potential pathway involves the reaction of methane with sulfur-containing volcanic gases. Methane is abundant in the atmosphere, confirmed at a concentration of 1%. If volcanic vents release hydrogen sulfide, and this hydrogen sulfide encounters methane under appropriate conditions, chemical reactions could yield organic sulfur compounds. Higher temperatures would favor the formation of different products compared to lower temperatures. A specific temperature range might promote the synthesis of dimethyl sulfide. Laboratory experiments have investigated this possibility. Researchers mixed methane and hydrogen sulfide and subjected them to various temperatures. At temperatures between 500 and 700 degrees Celsius, a variety of organic sulfur compounds were generated. Carbon disulfide was detected. Carbonyl sulfide was detected. Methyl mercaptan was detected. Dimethyl sulfide was also detected, but only in trace amounts. The resulting mixture of products was complex, yielding numerous molecules simultaneously. This is a typical characteristic of abiotic chemistry. Biological processes tend to produce specific molecules with high efficiency, whereas abiotic processes tend to generate a broad spectrum of substances simultaneously and inefficiently. The proposed volcanic pathway encounters quantitative challenges. Maintaining a concentration of 10 parts per million of dimethyl sulfide in the atmosphere necessitates a continuous production rate that matches the destruction rate. Scientists have calculated the required volcanic outgassing rates. They estimate that hydrogen sulfide emissions would need to surpass Earth's total volcanic output by factors of hundreds or thousands. This ocean world would therefore need to be one of the most volcanically active celestial bodies in the observable universe. While not entirely impossible, this scenario seems improbable. Furthermore, there is the issue of methane. Methane itself requires an explanation. On Earth, the majority of atmospheric methane originates from biological sources, produced by methanogenic bacteria or released during the decomposition of organic matter. A smaller portion is derived from geological processes, such as serpentinization, where water reacts with specific rock types to produce hydrogen and methane. However, these geological sources typically yield relatively modest quantities. The 1% methane concentration on this ocean world exceeds what abiotic processes generally produce. If volcanoes are responsible for generating the methane, they must also produce dimethyl sulfide through the same mechanisms. This would present a self-consistent abiotic scenario. However, it hinges on extraordinarily active volcanism and specific chemical conditions that optimize the production of organic molecules. Current models struggle to satisfy both of these requirements simultaneously. Either the volcanic activity is insufficient to produce adequate quantities of gas, or the temperatures are too high for organic molecules to survive. Another potential volcanic pathway involves the chemistry of intermediate water. Volcanic gases dissolve into the ocean water. These dissolved gases then react with each other in solution rather than in the atmosphere. Aqueous chemistry permits different reaction pathways. Some reactions that are ineffective in the gas phase proceed efficiently in water. It is conceivable that dissolved hydrogen sulfide and dissolved organic molecules combine within the ocean to form dimethyl sulfide. Subsequently, the dimethyl sulfide evaporates into the atmosphere. This aqueous pathway presents its own set of difficulties. Ocean chemistry is regulated by dissolved minerals. Seawater on Earth typically has a pH of around 8, indicating a slightly alkaline environment. This pH range significantly influences which chemical reactions can occur. The formation of dimethyl sulfide generally favors acidic or neutral conditions, not alkaline ones. However, the pH of this ocean world's water is unknown. If volcanic activity were to acidify the ocean, that might facilitate dimethyl sulfide production. Nevertheless, acidic oceans would dissolve carbonate minerals and exhibit different atmospheric carbon dioxide levels. The available observations do not strongly support extreme pH conditions. The reality is that scientists have not yet identified a volcanic pathway that fully accounts for the observed phenomena without invoking extraordinary circumstances. Volcanic sources might contribute to the dimethyl sulfide levels, potentially explaining a portion of the observed signal. However, accounting for the entire observed concentration would necessitate either extreme volcanic activity or highly specific chemical conditions, or both. In terms of explanatory simplicity, biological origins remain the more straightforward hypothesis. What if the star itself renders this planet uninhabitable? Red dwarf stars are known for their violent nature. They erupt with massive flares, releasing energy equivalent to billions of nuclear bombs. These stellar flares bombard nearby planets with X-rays, ultraviolet radiation, and streams of charged particles. Such flares occur with considerable frequency, sometimes multiple times daily during active periods. This phenomenon is well documented through observations of thousands of red dwarf stars. We have witnessed their eruptions and measured the released energy. The danger they pose is substantial. Why do red dwarfs exhibit such frequent flaring activity? The explanation lies in their magnetic field generation mechanisms. Stars create magnetic field through dynamo processes, where the movement of electrically conductive plasma generates electric currents, which in turn produce magnetic fields. On our Sun, the dynamo operates within a shell near the surface. On red dwarfs, however, the dynamo operates throughout the entire star because they are fully convective. Hot plasma from the core ascends to the surface, while cooler plasma from the surface descends to the core. This circulation creates powerful, tangled magnetic fields. These magnetic fields store immense amounts of energy. Periodically, magnetic field lines become stressed and twisted. When this stored energy is released suddenly, a flare occurs. Material heated to millions of degrees erupts from the star's surface. Radiation across the entire electromagnetic spectrum is emitted outward. For a planet orbiting very close to such a star, this event is catastrophic. The radiation arrives within minutes, offering no warning and no opportunity for shelter. What is the effect of this radiation on planetary atmospheres? Ultraviolet light and X-rays strike the upper atmosphere, ionizing molecules and atoms. Ionization involves the removal of electrons from atoms, resulting in the creation of charged particles. These charged particles are highly reactive and capable of breaking apart molecules. Complex organic molecules are particularly susceptible to destruction. On Earth, our planet's magnetic field and substantial atmosphere shield us from solar flares. Mars, lacking a strong magnetic field and possessing a thin atmosphere, has partly experienced atmospheric stripping over billions of years due to the solar wind. This ocean world orbits considerably closer to its star than Mars does, orbiting the Sun. The flares strike with greater intensity, and the radiation is more potent. If the planet lacks a magnetic field, its atmosphere is directly exposed. Scientists estimate that over billions of years, a red dwarf star could strip away several Earth masses of atmosphere from a nearby planet. The fact that this ocean world has retained its atmosphere suggests either the presence of a magnetic field, or its gravitational pull is sufficiently strong to retain atmospheric mass despite ongoing losses, or the star is less active than typical red dwarfs. The presence of magnetic fields is contingent upon a planet's internal structure. Earth possesses a magnetic field due to the convective motion of its liquid iron core, which generates a dynamo similar to stellar dynamos. Rocky planets with solidified cores tend to lose their magnetic fields. This ocean world is massive enough that it might still retain internal heat from its formation. If it possesses a liquid metallic core, it could generate a magnetic field. However, no direct observations confirm this. We are currently unable to measure magnetic fields on such distant planets. We can only infer their presence or absence through indirect evidence. Even if a magnetic field exists, stellar flares still pose significant challenges for life. While the radiation might not completely strip away the atmosphere, it can penetrate sufficiently deep to impact surface conditions. On Earth, the ozone layer absorbs harmful ultraviolet radiation. Oxygen in the atmosphere forms ozone. Without ozone, ultraviolet radiation reaches the surface unimpeded. Organisms on the surface would require protective mechanisms, such as robust cell walls, radiation-resistant proteins, or dwelling underwater where water can absorb the radiation. The frequency of flares is a critical factor. If flares occur daily, life must contend with constant bombardment. If flares occur annually, there are extended periods for recovery. Observations of this particular red dwarf indicate it is relatively old, approximately 2.4 billion years. Older red dwarfs tend to be less active than younger ones. Stellar activity diminishes over time as stars spin down and their magnetic fields weaken. It is possible that this star has become less volatile, such that its flares no longer pose a severe threat to planetary atmospheres. However, even quiescent red dwarfs can flare occasionally. A single massive flare could temporarily obliterate biosignature gases in the atmosphere. If dimethyl sulfide is destroyed during a flare, subsequent observations would reveal lower concentrations. Multiple observations spread across several months would help determine whether concentrations fluctuate in correlation with stellar activity. To date, the available data comes from only 2 observation windows. Further observations might reveal temporal variations indicative of flare impacts. What about the gentler, yet persistent, stellar wind? All stars emit a stellar wind, which is a continuous stream of charged particles flowing outward. Our Sun generates solar wind that travels at approximately 1 million miles per hour. This wind gradually carries away stellar mass. Over the Sun's lifetime, it has lost a minuscule fraction of its total mass through this process. The stellar wind also carries magnetic field lines that interact with planetary magnetic fields. Earth's magnetosphere effectively deflects most of the solar wind around our planet. Particles that manage to penetrate the magnetosphere are responsible for creating auroras at the poles. This is a well-understood aspect of space physics, confirmed by decades of measurements from spacecraft. Red dwarf stars emit less massive stellar winds than the Sun in terms of total mass loss. However, their planets orbit so closely that the density of the stellar wind becomes a significant factor. Imagine the difference between standing in a gentle breeze and standing in that same breeze while pressed directly against the fan producing it. This ocean world is situated 13 million miles from its star, whereas Earth is 93 million miles from the Sun. The planet orbits 7 times closer relative to the star's size. At this proximity, the density of the stellar wind is considerably higher. The stellar wind erodes planetary atmospheres through several mechanisms. Firstly, momentum transfer. Fast-moving particles collide with atmospheric atoms and molecules. In some instances, these collisions impart sufficient energy for atmospheric particles to overcome the planet's gravitational pull. This process is known as sputtering. Gradually, atoms are dislodged and ejected into space. Over millions of years, sputtering can remove substantial amounts of atmospheric mass. Secondly, charge exchange. Stellar wind comprises ionized particles, predominantly protons. When these ions encounter neutral atoms in an atmosphere, they can capture electrons. The newly ionized atmospheric atoms then become subject to magnetic fields. They are swept up by the stellar wind and carried away. This process is particularly effective at removing light elements like hydrogen and helium, which are easily ionized. Thirdly, atmospheric heating. The stellar wind deposits energy into the upper atmosphere, causing it to heat up. Heated atmospheric particles move at higher velocities. Some reach escape velocity and drift away from the planet. This thermal escape mechanism is most pronounced for light elements, with hydrogen escaping fastest, followed by helium. Heavier elements such as nitrogen, oxygen, and carbon escape more slowly, but they still escape. Mars serves as a cautionary example. Mars once possessed a thicker atmosphere, as evidenced by ancient river valleys and lake beds. Over billions of years, the solar wind stripped away most of its atmosphere. Mars lost its magnetic field early in its history when its core solidified. Without magnetic protection, its atmosphere became vulnerable. Today, Mars has less than 1% of Earth's atmospheric pressure. The planet became arid and frozen. This is supported by data from rover missions and orbiting spacecraft that have directly measured atmospheric loss rates. Could this ocean world suffer a similar fate? The presence of a hydrogen-rich atmosphere might actually provide some protection against atmospheric loss. Hydrogen is the lightest element and occupies the uppermost atmospheric layers. The stellar wind primarily interacts with this hydrogen, stripping it away, but leaving heavier molecules deeper within the atmosphere largely unaffected. This massive hydrogen envelope acts as a sacrificial shield. As long as the planet can replenish hydrogen from below, it could potentially sustain its atmosphere indefinitely. However, the source of this replacement hydrogen is critical. If the planet harbors a hydrogen-rich interior, convection and outgassing could continuously release hydrogen. Alternatively, if the planet contains water, that water could be dissociated into hydrogen and oxygen. The hydrogen would escape, while the oxygen would react with surface materials or become incorporated into molecules. This process would gradually dehydrate the planet over billions of years. Venus exemplifies this process, having lost an ocean's worth of water through hydrogen escape, becoming desiccated under a runaway greenhouse effect. Scientists estimate atmospheric loss rates using models that incorporate parameters such as stellar wind properties, planetary gravity, magnetic field strength, if present, and atmospheric composition. For this ocean world, the estimated loss rates vary considerably depending on the assumptions made. Optimistic models suggest atmospheric loss rates low enough for the planet to retain its atmosphere for billions of years. Pessimistic models predict rapid atmospheric depletion within hundreds of millions of years. The fact that an atmosphere persists after 2 billion years provides a constraint, indicating that loss rates cannot be as high as the pessimistic models suggest. However, beyond this conclusion, considerable uncertainty remains. What about the unusual elliptical orbit? Recall that the orbital eccentricity of 0.09 signifies that the planet's distance from its star varies by 12% between its closest and farthest approaches. This translates to a 43% variation in the amount of starlight received. Imagine if Earth's seasons operated in such a manner. Instead of gradual temperature shifts driven by axial tilt, we would experience extreme fluctuations every few months. This is confirmed by orbital mechanics calculations derived directly from precise timing measurements of planetary transits. The orbital period is 33 days. This means the planet transitions from maximum starlight intensity to minimum intensity in approximately 16 days, and then back to maximum in another 16 days. For life, this imposes a punishing rhythm. Organisms would struggle to adapt to high temperatures and intense light levels, only to have conditions reverse abruptly, with temperatures dropping and light dimming. Before adaptation can be completed, the conditions would reverse again. It is akin to trying to acclimatize to both summer and winter simultaneously. On Earth, seasonal changes occur slowly enough for life to adapt. Trees sense changes in day length months before winter and prepare by migrating nutrients and shedding their leaves. Animals build up fat reserves or migrate to warmer climates. These adaptations are effective because seasons last for months and repeat predictably each year. However, 33-day cycles are too rapid for most biological adaptations. A tree cannot grow leaves, shed them, and then regrow them within a period of a few weeks. Microbial life might fare better under such conditions. Bacteria reproduce rapidly, with generation times ranging from hours to days. Within 33 days, bacteria can undergo dozens or even hundreds of generations. This facilitates rapid evolution. Bacterial populations can adapt to changing conditions through natural selection operating in near real time. Beneficial mutations can spread throughout the population within a single orbital period. Complex organisms with generation times measured in years cannot adapt this quickly. The temperature fluctuations also affect ocean circulation. Warmer water expands, while cooler water contracts. As the planet traverses its orbit, the ocean literally swells and shrinks. This creates tidal forces distinct from gravitational tides. These thermal tides would drive currents, leading to mixing between surface and deep ocean waters. Such mixing might distribute nutrients, benefiting marine life, or it could disrupt stable water layers, harming organisms adapted to specific depths. Atmospheric chemistry also changes in response to temperature variations. Chemical reaction rates approximately double for every 10 degrees Celsius increase. As a general rule, if surface temperatures fluctuate by 20 degrees Celsius over the orbital cycle, reaction rates can vary by a factor of 4. The destruction rate of dimethyl sulfide would occur 4 times faster at orbital closest approach compared to its farthest point. Production rates would also vary if they are dependent on temperature-sensitive biological processes. The consequence is that atmospheric concentrations might exhibit oscillations synchronized with the planet's orbit. Webb observations captured snapshots at specific moments during the orbit. The data represents the atmospheric conditions present when the planet happened to transit its star. If concentrations vary significantly, different observations might indicate different levels of dimethyl sulfide. Comparing multiple observations could reveal whether concentrations are stable or variable. To date, 2 observations have yielded consistent results, but 2 data points are insufficient to definitively rule out variability. The elliptical orbit also impacts the concept of the habitable zone. Traditionally, the habitable zone is defined as a range of distances from a star where a planet with an Earth-like atmosphere could maintain liquid water, assuming circular orbits. For elliptical orbits, the planet spends portions of each orbit inside and outside the traditional habitable zone. This water-covered exoplanet journeys on an orbit that oscillates just within and just beyond the zone where liquid water could potentially exist. Whether water can remain in its liquid state under such fluctuating conditions hinges on the ocean's capacity to adapt swiftly to these atmospheric shifts. The substantial thermal inertia of water acts as a stabilizing influence. Oceans do not instantaneously warm or chill. They exhibit a temporal lag behind alterations in the atmosphere. Consequently, even with drastic fluctuations in air temperatures, the surface temperature of the ocean might only experience minor deviations of a few degrees. The deep ocean, however, could remain remarkably insulated from these temperature swings. Life might thrive within these more stable, deeper strata, shielded from the vagaries of orbital changes. Alternatively, organisms could engage in vertical migration, perpetually seeking out optimal temperature layers as they ascend and descend. To definitively resolve this ongoing debate, what specific confirmation do future observations need to provide? The forthcoming observations must clearly distinguish between dimethyl sulfide and dimethyl disulfide. The existing data presents absorption characteristics that are congruent with either molecule, or potentially both. These are chemically related compounds, exhibiting similar spectral signatures within the observed range of wavelengths, though they are not identical. Expanding the observational scope to include longer wavelengths would reveal the distinguishing features. Dimethyl disulfide possesses potent absorption bands between 6 and 7 microns, a characteristic absent in dimethyl sulfide. Observing at these specific wavelengths would pinpoint which molecule is present. This distinction is significant because, on Earth, dimethyl sulfide and dimethyl disulfide originate from slightly different processes. Dimethyl sulfide is predominantly generated from the decomposition of phytoplankton breaking down dimethyl sulfonylpropionate. In contrast, dimethyl disulfide primarily arises from bacterial metabolic activity. Identifying the presence of one, the other, or both would serve to narrow down the potential types of organisms that could exist there. While all are considered biosignatures, they each convey distinct narratives about the functioning of the ecosystem. Furthermore, the observations must enhance their statistical reliability. The present level of certainty stands at 3 sigma, corresponding to a 99.7% probability, implying a 0.3% chance of error. The scientific community, however, mandates a 5 sigma threshold for discovery, which reduces the probability of error to a mere 0.6%. To attain this 5 sigma level, additional observation time is indispensable. Each subsequent transit observation contributes to refining the signal-to-noise ratio. With the addition of 2 or 3 more transits, researchers estimate they could achieve the coveted 5 sigma level. The 5 sigma benchmark is not an arbitrary figure. It represents the point at which random chance becomes so improbable that systematic errors become the principal concern. At 3 sigma, a pattern might appear due to sheer luck. At 5 sigma, luck is effectively eliminated as an explanation. Any remaining uncertainty then pertains to the accuracy of instrument calibration or the completeness of theoretical models. Such questions can be addressed through independent verification and alternative analytical methodologies. Independent verification entails separate teams scrutinizing the same datasets. Scientific findings gain greater credibility when multiple groups arrive at the same conclusions employing divergent analytical techniques. The raw data from the telescope is publicly accessible after a brief proprietary period, allowing anyone to download and analyze it. Indeed, several teams have already investigated the dimethyl sulfide signal and, in general, concur on its authenticity, although interpretations continue to be debated. Access to more data would provide a richer foundation for analysis and aid in resolving existing disagreements. The observational efforts should also actively seek out other potential biosignature candidates. Methyl chloride is predicted to be a biosignature on Hycean worlds, forming when organisms integrate chlorine into organic compounds. On Earth, our oceans harbor methyl chloride produced by marine algae and kelp. Its detection on this ocean planet would furnish independent corroboration of biological activity. Conversely, its absence could suggest that abiotic processes are the dominant drivers. Oxygen remains the preeminent biosignature on Earth, with photosynthetic organisms releasing it as a byproduct. It accumulates in the atmosphere because continuous replenishment outpaces its chemical degradation. Detecting oxygen on an exoplanet would constitute compelling evidence for life. Although abiotic oxygen production is conceivable through water photolysis, this particular ocean world exhibits no oxygen, which, paradoxically, aligns with the Hycean hypothesis. In hydrogen-rich atmospheres, oxygen would not accumulate, even if produced by organisms, as it would rapidly react. Seasonal variations warrant careful examination. If concentrations of biosignatures fluctuate over time, this could reflect biological cycles, orbital dynamics, or the influence of stellar activity. Earth's atmosphere displays seasonal shifts in carbon dioxide levels corresponding to the growth and decay of plants. Analogous cycles on another world would imply that biology is responding to environmental cues. Alternatively, consistent concentrations over months or years might indicate a stable equilibrium between production and depletion. The ultimate objective extends beyond merely confirming the presence of dimethyl sulfide. It involves discerning its origin. This necessitates the detection of a suite of molecules that, collectively, unequivocally point to biological processes or clearly signify abiotic origins. No single molecule can definitively prove the existence of life, but assemblages of molecules whose existence is only logically explained by biological production would be highly convincing. What threshold must we surpass before confidently asserting the discovery of extraterrestrial life? The stakes could not be higher. Announcing the detection of alien life would represent one of the most momentous occasions in human history, providing an answer to a question humanity has pondered for millennia. Are we alone? Such a revelation would fundamentally reshape our understanding of philosophy, religion, science, and our place within the cosmos. A misstep, however, would be catastrophic. Declaring the presence of life where none exists would irrevocably damage scientific credibility, casting doubt on future genuine discoveries. This is precisely why scientists demand a 5 sigma level of certainty. 5 sigma signifies that the probability of being mistaken due to random chance is less than 1 in 3.5 million. This is akin to flipping a coin and obtaining heads 22 consecutive times, an event so exceedingly improbable that one would confidently assume the coin is rigged. In the realm of particle physics, 5 sigma was the standard for confirming the existence of the Higgs boson. In astronomy, it was the criterion for announcing the detection of gravitational waves. For the prospect of alien life, anything less would be deemed irresponsible. This is not an official policy, but rather a consensus forged through hard-won experience within the scientific community. History serves as a cautionary teacher. In 1996, NASA scientists announced the potential discovery of fossilized bacteria within a Martian meteorite. This news garnered worldwide attention, but subsequent analyses revealed alternative interpretations. What initially appeared to be bacterial fossils might have been mineral formations, and what seemed to be biological markers could have been contamination. Today, the prevailing scientific consensus is that the evidence remains insufficient. This episode impressed upon all involved the necessity of demanding more robust proof before making audacious claims. More recently, the detection of phosphine on Venus generated considerable excitement. In 2020, scientists reported identifying phosphine gas in Venus's atmosphere. On Earth, phosphine is produced by bacteria or industrial processes. Its presence on Venus suggested the possibility of microbial life existing within its clouds, but subsequent reanalyses cast doubt on the initial detection. The spectral signature might have actually been sulfur dioxide, misidentified. The claimed phosphine might not be present at all. Confidence eroded significantly, shifting from a strong detection to one of uncertainty. These initial false starts may have had ramifications. Public interest in astrobiology remains high, but a degree of skepticism has increased. Media outlets now approach new claims with greater caution. Scientists face pressure to ensure absolute certainty before going public. The ongoing research into dimethyl sulfide benefits from these lessons learned. The investigative team consistently emphasizes a cautious approach. They are not asserting that life has been found. Rather, they are identifying a biosignature that necessitates explanation. This distinction is crucial. A biosignature is a signal that is consistent with life, but does not constitute definitive proof. Other explanations might exist. The signal could be misinterpreted, or observational errors could be present. Only after exhausting all alternative hypotheses and repeatedly confirming the signal can scientists contemplate declaring a discovery. This rigorous process inherently requires time and considerable patience, often necessitating additional observations that may take years to acquire. Public communication presents a significant challenge to this methodical approach. the instant preliminary results hint at the possibility of extraterrestrial life. Media coverage intensifies, often simplifying complex findings and losing valuable nuance. The public may come to believe that scientists have discovered aliens when, in reality, they have identified a signal that might indicate the presence of life. Effectively managing expectations becomes paramount. Overstating findings can lead to public backlash, while understating them risks discoveries being overlooked. Striking this delicate balance is exceptionally difficult. Some argue that the 5 sigma threshold is overly stringent for biosignatures. Unlike particle physics experiments, which can be replicated with relative ease, astronomical observations are constrained by limited telescope time. Adhering strictly to 5 sigma might delay potential discoveries for decades, even when the signal itself is demonstrably real. The question arises, should society defer acknowledging probable discoveries until absolute certainty is achieved? Conversely, others contend that premature announcements cause more harm than delays, arguing that it is preferable to be late and correct than early and mistaken. This ocean world resides precisely at this critical juncture. The signal is robust, and the interpretation is reasonable. Alternative explanations struggle to fully account for the observations, yet lingering doubt persists. Perhaps something unexpected is occurring, or the current models fail to capture essential chemical processes. It's conceivable that multiple coincidences have aligned to mimic a biosignature. Attaining 5 sigma would not entirely eliminate these possibilities, but would render them highly improbable. The forthcoming year will be pivotal. If additional observations reach the 5 sigma standard, and if alternative explanations continue to fall short, the scientific community will confront a significant decision. At what precise point does probability transition to certainty? At what juncture do we accept that life beyond Earth has been detected? This decision will not be the prerogative of a single individual or team. It will emerge from a broad consensus across the entire field of astrobiology. We stand on the precipice of knowing. 124 light-years away, a planet orbits a faint red star. Within its atmosphere, chemicals are being generated that, on Earth, are exclusively produced by life. Something is occurring there that we cannot yet explain without invoking biological processes. The telescope remains focused, observations are accumulating, and certainty is steadily increasing. Within months or years, we will ascertain whether this ocean world is inhabited or if we have once again been misled. Regardless of the outcome, we have entered a new epoch, an era where discovering life elsewhere is no longer a mere fantasy, but a scientific inquiry fueled by tangible data and approaching real answers. The question that has captivated humanity since our earliest gazes towards the stars may finally be answered. We are close. So very close.